Hello there and welcome to Science for Sleep, where curiosity settles in beside you and the universe becomes a quieter place to explore. Tonight we're drifting towards something a little stranger than usual. Not a star, not a comet, not even a black hole, but something almost hard to imagine. A place in the universe where there's almost nothing at all. A region so empty that even astronomers had to double-check their instruments to be sure it was real. A place called the Booty's Void. You might picture space as mostly empty already, but this is emptiness on a different scale entirely. The kind of emptiness that makes the rest of the cosmos look crowded by comparison. The kind of emptiness that stretches so far and so wide that it challenges our understanding of how the universe even formed. Yet somehow this enormous hollow in the sky sits not impossibly far beyond reach, but surprisingly close in cosmic terms. Close enough that we can feel a little thrill of strangeness just knowing it's out there. A quiet giant of near-nothingness wrapped in the scenery above our heads. Before we drift into that vast hollow, I'd love to know where you're listening from tonight. Maybe you're settling into bed somewhere where the evening air feels cool and still. Maybe you're stretched out on a sofa, letting your thoughts slow down after a long day. Or maybe you're listening from somewhere with a bright sky and city lights, where the stars are shy but still there, waiting behind the glow. Wherever you are, thank you for being here and letting your mind wander with me for a little while through this gentle corner of science. And if this helps you unwind or gives you a bit of peace as you rest, I'd be grateful if you liked the video or subscribed. It helps others find this quiet space too, especially those who might need a slower pace or a calming escape before sleep. Now let's take our time, no rush, as we begin to drift toward the idea of the Booty's Void. When astronomers look at the universe, they don't just see stars scattered randomly. There's structure beneath the surface, a kind of cosmic architecture that weaves galaxies into clusters and threads them into immense filaments stretching across space. If you could step back far enough, galaxies would stop looking like isolated islands and start looking like beads on long strands. Between those strands are gaps, some small, some large, some surprisingly deep. These are called voids, and they're natural parts of the universe's layout. But among all the voids discovered, one stands out. Not because it's simply bigger, but because it's larger in a way that seems almost unreasonable. The Booty's Void sits about 700 million light-years away. That's far on a human scale, but modest when compared with the universe's overall size. It spans nearly 300 million light-years across. To put that into something we can grasp, imagine travelling from one side of the Milky Way to the other. That would take you around 100,000 light-years. Now imagine doing that almost 3,000 times back to back without bumping into galaxies the way you normally would. Travelling through the Booty's Void would feel like drifting through a desert where the sand has blown away and only the wind remains. Hardly any stars, hardly any clusters, almost no landmarks at all. Just the rare galaxy, lonely and distant, like a tiny streetlight in an enormous fog. But we're getting ahead of ourselves. Before we sink into the centre of that emptiness, it helps to ease in slowly, the way you might ease down into warm water. So let's begin by imagining the night sky in a way you've probably never looked at it before. When you step outside and glance up, you see stars speckled across the darkness, some brighter, some dimmer, some forming patterns that cultures have traced for generations. But that starlit dome isn't a smooth layer filled with evenly spaced lights. It's more like a map that hides enormous distances between each pinprick of brightness. The stars you see in the sky are only the ones close enough for the human eye to catch. Beyond them are countless others, and beyond those lie galaxies, each containing billions of stars of its own. And beyond even that, there are clusters of galaxies bound together by gravity, creating immense communities of cosmic neighbourhoods. The Booty's Void is one of the places where those neighbourhoods thin out dramatically, almost as if the universe forgot to place galaxies there. When the void was discovered in the early 1980s, astronomers were charting galaxy positions to understand how matter was distributed on enormous scales. They expected to find some variation, because the universe is not perfectly uniform. However, no one expected to find a region so large and so empty that it seemed like someone had carved out a spherical section of space and left behind a hollow seam in the cosmic web. When they first saw the gap, they checked for errors, missing data, faulty observations, anything that could explain the absence. But the more they looked, the clearer it became. The void was real. As we begin this slow journey through the idea of such an enormous gap, it helps to think about what emptiness means in astronomy. In daily life, emptiness might mean a quiet room, an untouched beach, or a calm field. In space, emptiness isn't a quiet moment or a peaceful landscape. It's a lack of gravity anchors, a lack of material, a lack of the things that normally build structure. Most regions of space, even the empty ones, contain stray stars, rogue planets, dust, and particles drifting from place to place. But a void is a region where the density of matter drops far below the cosmic average. Instead of clusters and filaments, you get mostly vacuum with the occasional stray galaxy passing through like a wanderer who took a wrong turn on the way to somewhere brighter. The Bootes void has become one of the most famous examples of this kind of sparse region. Part of that comes from its size, but part also comes from the way it stands out in the larger diagram of the universe. If you imagine the cosmos mapped as bubbles and filaments, the void looks like a cavity between great walls of galaxies. It's almost like a room carved out inside a sprawling cosmic building. The universe around it is rich with structure, threads of matter stretching across vast distances. But the void itself is a hollow that interrupts the pattern, a dark pause in the chant of galaxy formation. You might wonder how such a thing could form. How do you get a region so large and so empty that it seems like the universe skipped it during construction? The leading explanation comes from the way matter behaved in the early cosmos. After the Big Bang, matter wasn't evenly spread. There were slight fluctuations, tiny variations in density, some areas with more matter, some with less. Over time, gravity amplified those differences. Regions with a little more matter pulled in more. Regions with slightly less matter lost material to their neighbours. Over billions of years, dense regions became filaments and clusters, while low-density regions stretched into voids. The Bootes void, by this reasoning, might simply be an extreme example of this natural process. That explanation makes sense mathematically, but emotionally it's hard to grasp. We're used to thinking of the universe as filled with wonders, not missing pieces. We think of stars, nebulae, galaxies, and swirling clouds of gas. But here is a region where almost none of that exists. It's natural to imagine it as cold or lonely, but in truth, it's neither. It's not lonely because emptiness doesn't feel loneliness, and it's not cold because cold requires matter to cool. The void is simply space in one of its quietest forms, a region where the universe is less busy, less crowded, less tangled, a region where a star might shine without close neighbours to compete with, a region where galaxies, if present at all, might drift for millions of years without meeting another. It's fascinating to think about what it would look like if you lived inside such a place. If a civilization somewhere in the Bootes void were to look up at their sky, the view would be dramatically different from ours. Instead of a Milky Way stretching overhead, they might see a faint smattering of distant glimmers. Their night sky would be a sparse scattering of points, each separated by enormous distances. Without many nearby galaxies, their sense of the cosmos might be very different. Perhaps they'd grow up believing the universe was mostly empty, only later discovering the busy regions far beyond their own isolated bubble. As we let that idea settle in, you might be thinking about what it means that this enormous hollow sits not too far from our cosmic neighbourhood. It doesn't threaten us. It doesn't pull us in. It doesn't distort our daily lives in any way. But knowing it's there changes how we imagine the universe. It reminds us that the cosmos isn't a perfect grid. It's not evenly patterned. It's a tapestry woven with dense threads and wide gaps. It has places full of activity and places where almost nothing has happened for billions of years. And even in that stillness, there is something strangely comforting. The void isn't empty because something went wrong. It's empty because that's how the universe arranges itself on grand scales. Some places form cities of stars, others remain quiet plains. The Booty's void invites us to think about cosmic structure in a way we don't often pause to consider. When you picture the universe, you might think of stars scattered across the dark like confetti. But when astronomers map galaxies on the largest scales, the universe begins to look more like a sponge or a honeycomb. Long corridors of matter surround deep hollows. The voids are part of that natural pattern. They create balance, giving the denser areas room to form and stretch. In some ways, the Boots void is a reminder that emptiness is just as important to the structure of the universe as fullness is. Without the gaps, the filaments wouldn't stand out. Without the hollows, the clusters wouldn't have space to grow. When most people imagine the universe, they picture something full of light. Galaxies spiralling with bright clusters of stars. Nebulae glowing in soft colours. The Milky Way arcing across the night sky in a pale, misty streak. Even if you've never seen the Milky Way clearly with your own eyes, the common idea of the universe is that it's bright, lively, and filled with distant suns. And that impression isn't wrong. On large scales, the universe contains an astonishing amount of light. Not just visible light, but microwaves, infrared radiation, X-rays, ultraviolet bursts, gamma rays, and radio waves, humming constantly through the dark. The cosmos is full of places that shine, pulse, erupt, flicker, and glow. Even a quiet galaxy, one that isn't forming many new stars, still emits a soft presence in the darkness. Because of this, astronomers spend most of their careers looking for light. They build telescopes designed not only to capture faint sources, but to measure the smallest variations in brightness. These instruments are sensitive enough to catch signals that have travelled billions of years across expanding space. The universe seems generous with photons, scattering them everywhere like seeds. So when astronomers stumble on a region where their lights have gone out, or perhaps never turned on in the first place, it stands out. It becomes something unusual, something worth examining closely. That contrast between the glowing universe and a region that is almost empty is what makes the Booty's void so striking. Not just because it lacks light, but because it lacks nearly everything that produces light in the first place. There are very few galaxies inside it, and the ones that do exist there appear lonely compared with the crowded clusters elsewhere. Most of space has at least some galaxies drifting through it. The Booty's void has far fewer than expected for a region of its size. That difference challenges assumptions about how matter naturally arranges itself. To get a sense of how unusual this is, it helps to picture what astronomers normally see when they map galaxies. They point their telescopes toward a section of the sky and record hundreds, sometimes thousands of galaxies in a single observation. They track how far away those galaxies are by measuring something called redshift, which is a way of understanding how fast stars and galaxies are moving away from us as the universe expands. When they gather enough data, they begin to see patterns. They notice that galaxies tend to cluster together instead of spreading out evenly. They notice long filaments where galaxies form lines, arcs, and networks. These patterns repeat across enormous distances, forming the large-scale structure of the universe. In these maps, the glowing points of galaxies create a visible web. Even though space is mostly empty, it has enough structure that astronomers expect to find some level of brightness almost everywhere they look. That's why the Booty's void became such an astonishing discovery. Instead of dots linking into lines or groups, astronomers found an enormous dry patch. A region where the familiar pattern broke down. A region almost completely different from what they had expected. To understand why this is surprising, imagine walking through a city at night. As you move through the streets, you see building lights, street lamps, cars passing by. There may be dark corners or quiet areas, but the city still emits a background glow. Now imagine stepping into a district that stretches for miles where there are no lights at all. No buildings, no roads, no movement. Just open space. The contrast would feel extreme. That's similar to the sensation astronomers experienced when they mapped the Bootes region and found almost nothing. The discovery didn't happen all at once. It took time for the data to reveal the scale of the emptiness. Early galaxy surveys in the 1980s were still building a picture of how galaxies were arranged on scales of hundreds of millions of light years. When researchers plotted points representing the locations of galaxies, a suspicious gap appeared. At first, they thought it might be an error. Perhaps the instruments missed something. Perhaps the calculations were off. But as more data arrived from different telescopes and different teams, the gap grew more defined. It wasn't a small pocket. It was a massive hollow, one of the largest known. The emptiness didn't mean there were 0 galaxies inside it. In fact, later observations found a few scattered ones. But the number was far lower than what would normally appear in a region that size. Instead of thousands of galaxies, there were only a few dozen. That difference is enormous from a statistical perspective. The Bootes void is so underpopulated that it challenges basic expectations about cosmic density. If galaxies were sprinkled randomly throughout space, the chance of such a large empty region forming on its own would be extremely low. That suggests something more structured is happening. The universe is not random. It follows patterns shaped by gravity, matter distribution, and the conditions of the early cosmos. The contrast between the bright regions of the universe and the Bootes void becomes even clearer when we examine how galaxies behave. Galaxies are not evenly distributed. They gather along filaments because those filaments contain a little more matter. Over billions of years, gravity pulls more and more material into these dense regions. The Bootes void, by contrast, seems to have had very little matter from the start. It's as though the universe gave it an uneven hand, leaving it with not enough material to form many galaxies. This leads to an interesting question. If the universe is full of light and energy, why would it leave behind such a large dark patch? The answer lies in the early fluctuations of the universe before galaxies existed. Just after the Big Bang, matter was not evenly spread. There were tiny differences in density, so small that it would have been impossible to detect with the naked eye, but large enough that gravity could work with them. Over time, these imperfections grew into the large-scale structure we see today. The Bootes void is likely the product of one of those low-density regions, stretched to an extreme size by billions of years of cosmic expansion. In a way, the Bootes void allows us to see how the universe naturally organizes itself when starting from slight imbalances. It becomes a record of what happens in a region that begins with less material than its surroundings. Where dense regions grow into large networks, the empty regions widen into voids. The Bootes void is simply a more pronounced example of this process. Another part of what makes this void stand out is how easily overlooked it is by casual observers. When you look up at the night sky, the Bootes constellation appears ordinary. There is nothing visually dramatic about the region where the void resides. The stars in that part of the sky seem normal. You wouldn't guess that an enormous hollow sits behind that familiar pattern. And that creates a strange sort of tension. The idea that an enormous structure can exist quietly behind something completely unremarkable. It's like discovering that behind the wall of your house is not another home or a yard, but an entire empty valley. You wouldn't know it unless you use specialized tools. That hidden nature is part of what fascinates astronomers. The Bootes void is invisible to the naked eye, yet it leaves a clear signature in large-scale galaxy maps. Its presence affects how matter flows on cosmic scales. It influences how galaxies cluster near its edges. It stretches the patterns around it into arcs and curves. This shapes the cosmic web in subtle ways. While it doesn't exert a strong gravitational pull of its own, its emptiness creates space for surrounding structures to form in distinct ways. The galaxy filaments bordering the void become more pronounced. In some regions, you can see the transition between a dense filament and the edge of the void with surprising clarity. It's a sharp change between a busy region and one that is quiet and still. If you could travel across the universe and approach the Bootes void from one of these filaments, you might notice the galaxies thinning out gradually before finally reaching the sparse interior. The boundary wouldn't be sudden, but the difference would become clear with distance. Far fewer galaxies, far more space between them. The stretch of emptiness would continue until you reach the scattered groupings deep inside the void. Those occasional galaxies found in the void are interesting in their own right. They appear somewhat isolated, as though formed from leftover fragments of matter that didn't make it into surrounding structures. How those galaxies formed remains a question. Some may have drifted in over billions of years from surrounding regions. Others may have formed from whatever small concentrations of matter existed inside the void at the start. The galaxies inside the void tend to be smaller and less active. They don't have the dense environments that encourage rapid star formation. Instead, they shine quietly, drifting through an ocean of darkness with no nearby neighbours to influence them. Their isolation makes them special because their development occurs almost entirely on their own. They experience fewer gravitational interactions and fewer collisions. They grow slowly and steadily, shaped mostly by internal processes rather than external disturbances. This contrast between the glowing regions of space and the Bootes void helps illustrate the diversity of cosmic environments. Some parts of the universe are crowded with galaxies, merging, colliding, and forming new generations of stars. Others are slow, quiet regions where galaxies evolve at a calmer pace. The Bootes void is an example of the latter taken to an extreme. Its emptiness gives astronomers a unique laboratory to examine how galaxies behave when left alone for long stretches of time. The absence of light also has another effect. It makes the Bootes void difficult to study directly. Astronomers rely heavily on light to understand distant objects. Without many galaxies, there are fewer sources to analyse. That means the void becomes a kind of observational challenge. Researchers must rely on indirect methods to understand what's inside it and how it formed. They map the distribution of galaxies along its edges. They study the movement of matter around it. They analyse the few galaxies within it to determine how old they are and how they evolved. In this way, the void becomes a puzzle, solved through patience, data, and careful mapping. Even though the Bootes void is astonishingly empty, it still belongs to the universe's overall structure. It's not a flaw or an anomaly. It's a natural result of how matter distributed itself over time. Its emptiness highlights the brightness of the rest of the cosmos. Without dark regions, the glowing ones wouldn't stand out as clearly. The Bootes void helps researchers understand the balance between dense and empty areas, showing how both contribute to the cosmic web. The presence of such a large empty region raises interesting questions about what might lie at its core. Not necessarily mysterious objects, but unusual conditions. If galaxies inside the void evolve differently because of their isolation, then studying them closely could reveal details about how star formation changes in low-density environments. It might reveal how galaxies age without frequent interactions. It might even give insight into how early fluctuations shaped the large-scale layout of the universe. Every part of the cosmos, even the quietest ones, offers clues. When you picture the universe as full of light, the Bootes void becomes a reminder that even in a glowing cosmos, there are pockets of stillness. It's like the universe takes a breath, leaving behind a wide, calm space between its busy structures. That wide space doesn't break the pattern, it completes it. It creates contrast that makes the bright parts easier to understand. When you look up at the night sky, you see something that feels complete. Even if you're in a city where the stars are faint, the sky still gives the impression of a finished picture. The constellations line up in familiar ways. The bright stars hold their places. The dark spaces between them seem like part of the design, not flaws in it. People have been mapping these shapes for thousands of years, creating stories that follow the patterns across the sky. And because of that long tradition, most of us think the night sky is a full, consistent backdrop. Even if you zoom out in your imagination to the galaxies beyond, it's easy to assume the universe must follow a similar level of uniformity. stars, galaxies and light scattered everywhere. But the more astronomers map the cosmos, the more they discover that the sky we see is only a thin layer of a much larger pattern, and that larger pattern has some surprising gaps. One of the most striking of those gaps is hidden behind the familiar stars of the Bootes constellation. If you've ever seen Bootes in the night sky, you might recognise it by the bright star Arcturus, one of the brightest stars visible from Earth. Arcturus is warm, steady and noticeable even from a light-polluted area. Around it, the constellation forms a shape that has become part of standard celestial charts. To the casual observer, nothing about Bootes looks unusual. It doesn't appear emptier than other regions. There's no visual clue that something enormous is missing behind those stars. Yet behind that ordinary patch of sky sits one of the largest cosmic voids ever discovered. This contrast between the visible sky and what lies beyond it creates a kind of quiet surprise. We expect dramatic cosmic features to come with dramatic appearances. A supernova announces itself with intense brightness. A nebula glows in colours that telescopes turn into famous images. A galaxy cluster shows up as a thick knot of lights. But the Bootes void hides behind a normal-looking part of the sky, almost as if the universe placed one of its strangest features behind a simple curtain. This missing piece doesn't stand out to the eye because stars in our own galaxy sit in front of it. When you're looking at a constellation, you're looking at stars that are relatively close on the cosmic scale. Some may be tens of light years away, others hundreds, but the distances are tiny compared to the hundreds of millions of light years between us and the Bootes void. The stars you can see act like decorations on a window, distracting from the fact that behind them lies a vast region almost completely empty of galaxies. Astronomers only realised something was missing when they began mapping galaxies at much greater distances. They weren't looking at stars within the Milky Way. They were looking far beyond, tracing the positions of galaxies across immense stretches of space. When they plotted those galaxy locations on charts, they noticed that one region showed almost no points. The emptiness wasn't obvious when looking at the night sky itself. It only revealed itself through careful measurements. That's part of why the void is sometimes called the universe's great missing piece, not because something was removed, but because something expected simply wasn't there. The night sky gives us a false sense of completeness. It shows only two things clearly: the stars of our own galaxy and the darkness between them. But that darkness is not a simple background. It contains distant galaxies too faint to see without instruments. It contains structures and patterns that play out over billions of light years. The galaxies that make up the large-scale structure of the universe are spread out in ways that don't match what the night sky suggests. The sky might look like a calm, evenly sprinkled scene, but the universe behind it is much more uneven. There are dense regions, thin stretches, and just enormous gaps. And the Bootes void is one of the most dramatic examples of those gaps. What makes the Bootes void feel like a missing piece is the scale mismatch. On the map of the universe, this void stands out as a huge blank region, but on the sky viewed from Earth, it looks ordinary. That disconnect reminds us that our direct senses aren't equipped to understand the universe's structure. Our eyes evolved to deal with distances across rooms or landscapes. Even standing on a mountain and seeing a horizon tens of miles away doesn't prepare the mind for distances measured in hundreds of millions of light years. Because our perspective is so limited, the sky hides more than it reveals. This is why large-scale surveys are so important in astronomy. Instead of relying on what the human eye can detect, telescopes record light from galaxies far beyond the Milky Way. When scientists compile that data into maps, the universe's true texture comes into view. It's not a smooth spread of galaxies. It's something more like a cosmic mesh, with dense knots and long threads surrounding broad open spaces. Those spaces are the voids. Most are modest in size compared with the Bootes void, but all of them play a role in shaping how matter organises itself. The Bootes void became famous because it was one of the first voids discovered to be so large that it seemed almost impossible. When astronomers saw how big it was, they questioned their assumptions. At first, it wasn't clear whether they had missed galaxies, miscalculated distances, or encountered an error in the data. Something this size wasn't expected. But as more surveys mapped the region, the evidence became undeniable. The void wasn't a measurement mistake, it was real. Thinking about the Boots void as a missing piece also helps make sense of how unusual it is. If you imagine the universe as a puzzle, most pieces are filled with galaxies and light. The void is like a section where the pieces look blank. Not because someone forgot to draw on them, but because that's simply how that part of the cosmos formed. The puzzle is still complete, but the picture includes areas with little detail. Those areas are just as important to the whole structure as the brighter ones. Even though the void is invisible without powerful telescopes, it shapes how we understand the universe. When we see that much space lacking galaxies, it forces astronomers to refine their models. It raises questions about how matter moved in the early universe. It also gives clues about how cosmic expansion affects empty regions differently from dense ones. Voids expand more quickly because there's less gravity holding them together. In dense regions, galaxies pull inward, slowing expansion. But inside a void, there's nothing to resist the expansion of space, so voids gradually become larger over billions of years. That means the Bootes void we see today is bigger than it would have been in the past, continuing to widen as the universe stretches. The missing piece of the sky is not just a visual gap, it's a dynamic part of cosmic evolution. It interacts with the structures around it through gravitational effects, even though it contains little mass of its own. It helps define the edges of the filaments that surround it. It influences how galaxies cluster near its boundary. By acting as a region where matter is scarce, it helps balance the regions where matter is dense. The void and the filaments aren't separate systems. They exist because of each other. Without voids, the dense regions wouldn't form the way they do. Without dense regions, the voids wouldn't expand into their distinct shapes. Sometimes people imagine cosmic voids as unnatural or mysterious, but they're not mysterious in the sense of needing hidden forces or unknown particles. They're mysterious because they challenge expectations. The Bootes void is so large that it pushes researchers to think more deeply about how the universe arranged itself. It also challenges the intuitive belief that the universe should look roughly the same in every direction. On very large scales, that belief holds true, but on medium scales, hundreds of millions of light years, there are dramatic variations. The night sky doesn't show you those variations directly. It shows only the stars of a single galaxy. Everything beyond that is too far and too faint for the eye alone. This means that the sky, as reassuring and complete as it looks, is missing enormous amounts of information. When you stand under the stars, you're only seeing the local neighbourhood. It's like looking at a map of the city you live in and thinking it represents the whole world. Behind that limited view lies a more complex structure. The Bootes void is one of the places that reveals just how different the larger structure can be. Even though the void is completely hidden behind an ordinary constellation, that only adds to the quiet strangeness of it. It's not a dramatic wound in the sky. It doesn't distort the stars in front of it. It doesn't cast a shadow or create a noticeable absence of light. It's simply behind everything we normally see. The stars that make up Bootes act like a kind of camouflage. They distract from the fact that beyond them lies an enormous region missing thousands of galaxies that statistically should have been there. This hidden nature has sparked curiosity among researchers. If one of the universe's largest empty regions can be hidden behind a normal-looking patch of sky, what else might be waiting behind other constellations? How many more large voids remain to be mapped fully? As observational tools improve, astronomers are finding more voids than they once expected. Some are almost spherical, like the Bootes void. Others are stretched or irregular. Together, they form part of the cosmic pattern that helps define where matter collects and where it does not. One of the most surprising things about the Bootes void is how subtle its presence is in the night sky. You could spend your entire life looking up at the stars, tracing constellations, and never suspect that a vast empty region stretches far beyond them. This contrast between appearance and reality is an important reminder that human senses are limited. Our eyes evolved to navigate Earth, not to interpret cosmic distances. Without telescopes, the Bootes void would remain completely unknown. Even with telescopes, it took careful mapping and statistical analysis to reveal its true size. The idea that such a large structure can remain invisible behind an ordinary arrangement of stars shows how much remains hidden in the cosmos. It also shows how much work astronomers have to do to uncover these large-scale patterns. The night sky is beautiful, but it is not a clear window into the universe's architecture. It is more like a surface layer. Everything beyond that surface requires tools, data, and time to uncover. Understanding that the Bootes void sits behind a familiar part of the sky also changes how we think about constellations. They're not regions of space, they're projections. The stars forming them aren't close to each other in reality, they just happen to line up from our point of view. Behind every constellation is a nearly infinite stretch of space filled with structures we can't see without assistance. Some of those structures are bright and active. Others, like the Bootes void, are quiet and sparse. Thinking of the void as the night sky's missing piece helps bring the rest of the universe into perspective. Even though it sits behind a set of stars that feel familiar and unchanged, it represents something far larger and less intuitive. It reminds us that behind every bright dot in the sky is a much deeper story. When astronomers set out to map the universe on large scales, most of them didn't expect surprises. They knew there would be patterns. They knew galaxies weren't evenly spread. They knew clusters and filaments would show up when they plotted the data. But they assumed that as long as they kept gathering information, the overall picture would become clearer and more predictable. After all, by the late 20th century, astronomy had already gone through several revolutions. Telescopes were powerful, detectors were sensitive, computers were becoming capable of handling larger data sets, and researchers were confident that the universe would reveal its structure steadily, piece by piece. The idea that they would stumble into a region that looked almost empty simply didn't fit their expectations. Most large-scale galaxy surveys at the time were focused on understanding how matter clustered across hundreds of millions of light-years. These surveys involved measuring the positions and distances of galaxies, often using redshift to determine how far away each galaxy was. When plotted correctly, the data formed three-dimensional maps that resembled vast networks of points. These networks looked surprisingly organised. Instead of random scatterings, the galaxies arranged themselves into long strands and sheets, surrounding large pockets of thinner regions. Researchers knew these pockets existed, but they expected them to be modest in size. They assumed voids were common but relatively small compared to the larger filaments and clusters. So when astronomers working on one of these surveys began examining a region behind the constellation Bootes, they didn't expect anything out of the ordinary. They were simply mapping another area of sky, adding more dots to the growing cosmic diagram. At first, the data seemed routine. Galaxies appeared as expected, with the usual variations in density. But as they continued to extend their survey deeper and wider, something peculiar began to stand out. The number of galaxies started to drop, not by a small amount, but dramatically. A region that should have contained many galaxies instead looked strangely empty. The first reaction wasn't excitement, it was suspicion. When you're dealing with enormous distances and faint objects, errors are always possible. Maybe the instruments failed to detect some galaxies. Maybe the survey method wasn't sensitive enough in that area. Maybe the bright stars in the foreground interfered with the measurements. Astronomers have to consider every technical possibility before deciding something unusual is happening. No one assumed an enormous void right away. They assumed a mistake. That mindset says a lot about how unexpected the discovery was. If someone finds a strange feature in a small data set, it might be easy to accept. But when the feature spans a region hundreds of millions of light-years across, the idea becomes harder to believe. The stakes are higher, the consequences for cosmic structure models are larger. So the first step was to double-check everything. The researchers went through the data repeatedly. They checked calibration settings. They reviewed the catalogue of galaxies used in the survey. They looked for regions where the telescope might have had trouble capturing light. But after layer upon layer of verification, the conclusion became difficult to avoid. The gap was real. Still, verifying something so unusual required more than one team. Independent surveys were needed to confirm the shape and size of the empty region. Other astronomers pointed their telescopes toward the same part of the sky, measuring redshifts and looking for hidden galaxies. As those results came in, they pointed to the same conclusion. The region behind Bootes had far fewer galaxies than expected. It wasn't perfectly empty, but it was significantly underpopulated. Eventually, enough data accumulated for the scientific community to accept that this gap was not an artifact. It was a real structure. The moment when astronomers realized that they had found one of the largest voids in the known universe wasn't dramatic or loud. It didn't involve a single discovery night or a sudden burst of enthusiasm. Instead, it was a gradual process. One observation led to another. Skepticism turned into cautious interest, and interest turned into recognition. The Bootes void had revealed itself slowly, in the steady pace of scientific work. But even though the moment lacked fireworks, the implications were far-reaching. A region that enormous and that empty challenged many assumptions about large-scale structure formation. When astronomers looked at the void's size, they realized it wasn't just a slightly larger gap. It was huge on a scale that confronted the idea of typical voids. Most voids are around 30 to 50 million light-years across. Some are larger, maybe up to 100 million light-years. The Bootes void, however, stretches close to 300 million light-years across. That makes it one of the most extreme examples of its type. In fact, when researchers compared it with predicted patterns from early cosmological models, its size appeared unusual enough to prompt new questions. Was this void the product of normal cosmic evolution, just scaled up? Or did something unusual happen in this region early in the universe's development? The researchers who first charted it were aware that large structures often reveal interesting details about how matter behaves. But finding an extreme void made them reconsider the balance between dense and empty regions. They expected voids. They didn't expect something that felt like an exaggerated version of one. The void was so large that some astronomers wondered if multiple smaller voids might have merged over time. In many ways, that idea made sense. Voids tend to grow as matter gets pulled toward denser regions. So it's possible that smaller voids expanded and eventually blended into a single, large one. This could explain how such a huge gap formed naturally, without requiring any unusual events. Still, confirming the void's size required tracing its boundaries. That was another challenge. Unlike galaxies, voids don't emit light. They don't have well-defined edges. Instead, their boundaries are inferred from where galaxies cluster more densely. So astronomers had to plot where the galaxies were and draw conclusions about the empty regions between them. Doing that over distances hundreds of millions of light-years wide required large data sets and consistent methods. As more surveys covered the same region, the boundary of the void became clearer. It wasn't perfectly spherical, but it had a roughly round shape. The sphere-like quality of the void made it even more interesting. It suggested a balance in how matter flowed around it. The moment when astronomers accepted the existence of the Bootes void didn't end the questions. It started a long process of trying to understand it. One of the first questions was whether galaxies inside the void existed at all. The region seemed so empty that some wondered if it might truly lack galaxies entirely. But further observations found a few galaxies scattered throughout. They were rare, but they were there. These galaxies became particularly important for studying the internal environment of the void. Galaxies inside voids experience isolation on a scale that most galaxies never encounter. They have fewer interactions, fewer collisions, and fewer gravitational influences from nearby neighbours. As a result, scientists began studying these isolated galaxies to understand how different their evolution might be compared with galaxies in crowded environments. The existence of these galaxies also helped confirm the void's presence. Their redshifts showed they were inside the expected region. Their distribution was sparse, exactly what you would expect in a low-density area. These small clues fit together to paint a picture of the void's internal structure. Even though it was overwhelmingly empty, it wasn't completely abandoned. A handful of galaxies wandered through it, shining quietly within its vast interior. One of the most interesting aspects of the Bootes void is how it sits within the larger cosmic web. It's surrounded by walls of galaxies, dense regions that mark its edges. These walls are not physical barriers, of course. They're simply the regions where matter collected instead of drifting into the void. But they create a clear contrast between the busy filaments and the quiet hollow inside. When astronomers look at the large-scale distribution, these walls show up as bright arcs or curves in the data. The void lies behind them like a dark interior room in a building, hidden behind visible walls. This contrast helps explain why the Bootes void feels like a discovery of nothing. The surrounding clusters and filaments are filled with light. They represent regions where gravity pulled matter together. Standing next to those busy areas, the void looks like a missing piece. And because astronomers expected some galaxies there but found very few, the sense of absence becomes even stronger. It's not just that the void is empty, it's that it's empty in a way that defies initial expectations. The discovery of the void also influenced how scientists approached the study of cosmic structure. It encouraged more detailed surveys, deeper mapping techniques, and broader statistical approaches. Instead of assuming uniformity on medium scales, researchers began looking for more extreme variations. The presence of such a large void suggested that the universe might contain other unusual features. That shift in thinking opened the door for even larger surveys, including modern projects that map millions of galaxies across vast distances. It's worth remembering that the discovery occurred at a time when the cosmic web was only beginning to be understood. Before then, the idea of the universe forming a complex pattern of filaments, clusters, and voids was still relatively new. The realization that the cosmos looked more like a web than a uniform spread of material was a major shift. The Bootes void helped reinforce that shift. Its existence made it clear that the universe could form extreme structures. Not everything was average. Not everything followed the typical pattern. There were outliers, and those outliers offered valuable information. When astronomers found the void, they weren't expecting to find nothing. They expected more dots on the graph, more galaxies, more structure. Finding almost empty space on that scale was something that required a moment of adjustment. It's similar to expecting to open a door and find a crowded room, only to discover an abandoned hall stretching far beyond what you imagined. Nothingness becomes unexpected when you anticipate activity. The absence of galaxies forced researchers to rethink how they interpreted the data. It made them more cautious with assumptions and more attentive to unusual findings. The void also highlighted the importance of comparing independent observations. Since the discovery was gradual, involving different teams and different instruments, it stands as an example of how careful science works. Nothing is accepted without confirmation, and in this case, the confirmation revealed something extraordinary. The discovery didn't come with fear or alarm, it came with curiosity. Understanding why such a large empty region exists helps astronomers refine models of cosmic evolution. It provides insight into how small variations in the early universe can lead to large differences billions of years later. It shows how matter naturally flows toward dense regions, leaving behind hollow spaces. It also raises questions about what it would be like inside such a region. What kind of galaxies could survive there, and how they might evolve differently? As the understanding of the void deepened, astronomers began considering whether the Bootes void was a single entity or the result of multiple smaller voids merging. That idea fits well with how voids evolve. Small fluctuations grow over time as matter moves away. If several small voids existed close to each other, gravitational effects and cosmic expansion could combine them into a larger one. This helps explain the void's size without requiring unusual initial conditions. It also fits into the broader picture of the universe as a dynamic structure where changes occur gradually over immense timescales. The discovery of the Bootes void had another effect. It encouraged astronomers to map more of the sky with greater precision. If such a large void could remain unnoticed behind a typical constellation, what else might be hiding in plain sight? That question motivated more ambitious surveys. Some later voids found were smaller or less dramatic, but together they reinforced the idea that the universe contains more variation than previously assumed. The empty region behind Bootes became a starting point for many later studies of cosmic emptiness. Scientists began examining voids more systematically, measuring their shapes, sizes, and distributions. They studied how voids interact with surrounding structures. They analysed the few galaxies inside them. Gradually, voids gained recognition not as oddities but as essential components of cosmic architecture. Even though the discovery process was slow and methodical, the final realisation was profound. The universe contained a vast region where expectations failed, where galaxies were scarce, and where emptiness stretched farther than anyone predicted. It didn't change how humans see the night sky, but it changed how astronomers see the universe behind it. When astronomers finally accepted the Bootes void as a real structure, one of the first reactions many of them had was simple disbelief. Not because the data seemed wrong anymore, but because the scale was hard to make sense of. They were used to voids. Empty regions are not unusual. Voids are a natural part of how matter organises itself across the universe. Dense areas pull in material. Less dense areas get left behind. This pattern creates a cosmic web. Bright, busy filaments and clusters separated by quieter pockets of emptiness. But the Bootes void wasn't just another quiet pocket. It wasn't even a little larger than expected. It was dramatically larger. It was a bubble so big that it challenged almost every intuition about how voids should form. To understand why this matters, it helps to think about how astronomers measure the significance of a structure. They compare its size, density, and shape to predictions from cosmological models. These models simulate how the universe evolved from the early stages after the Big Bang to the present day. In these simulations, voids appear naturally. They grow, merge, stretch, and become part of the web. But the typical voids that form in these models tend to fall within certain ranges. Their sizes vary, but most cluster around what you might call the average void scale. Some are bigger, some are smaller, but the distribution is fairly predictable. Then along comes the Bootes void, with a diameter close to 300 million light-years. Immediately that number signals something unusual. A void that large means a region where matter distribution in the early universe must have been significantly lower than average for it to expand into such a huge cavity. It's like finding a desert the size of a continent in a world where smaller deserts exist but nothing that extreme. You'd expect there to be some big deserts, but you wouldn't immediately expect one that takes up such a large fraction of the map. The comparison feels off, even if it fits within the allowed physics. Astronomers sometimes describe their reaction to the Bootes void as a moment of recalibration, not because it rewrote the laws of physics, but because it forced them to reconsider what counts as typical. When a structure exists that pushes the boundaries of expected size by such a dramatic amount, researchers look more closely at how rare it should be. If an event or structure is extremely unlikely, it raises questions about whether something unusual happened. But if it is rare yet still possible, it becomes a statistical outlier rather than a sign of something fundamentally wrong. The Bootes void sits in that difficult space between unlikely and impossible. It's rare, but not so rare that it breaks cosmological theory. Even so, calling it rare doesn't fully capture the way it stands out. It's not just the size. It's the emptiness relative to its volume. Most voids contain fewer galaxies than surrounding regions, But the Bootes void contains far fewer than expected for a structure that large. That makes it doubly unusual. Large voids exist, and sparse voids exist, but a void that is both extremely large and extremely underpopulated is something that demands explanation. This is what made many astronomers describe it as too big to make sense of when they first fully grasped its scale. To get an idea of why this felt so extreme, imagine scaling down the universe to something more familiar. Think of the cosmos as a vast landscape filled with forests. Some areas have thick trees, some areas have thinner patches, some areas have meadows with fewer trees. Now imagine a clearing so enormous that it stretches beyond the horizon. Not just a meadow, not even a valley, but an empty expanse that seems out of proportion with everything around it. Even if you know clearings exist, finding one that massive would make you stop and reassess how the landscape formed. That is what astronomers faced. They were already familiar with the forest of galaxies and the meadows of smaller voids. But the Bootes void was something like an open plain on a scale that felt out of balance with its surroundings. One of the explanations that emerged early on was the idea of void merging. This concept suggests that small voids that form in the early universe can grow and combine over time. Gravity pulls matter toward dense regions, which causes voids to expand as material drains out of them. If several small voids lie near each other, their boundaries can merge, forming a larger combined structure. This process can continue, turning multiple moderate voids into one large one. If the Bootes void formed through this mechanism, it wouldn't require unusual initial conditions. It would simply be the natural result of billions of years of evolution. But even with that explanation, the size remains impressive. It requires a sequence of events where several voids must form close together, expand at similar rates, and merge in a coordinated way. It's not impossible. It's just less common than typical cosmic evolution patterns. That difference between improbable and impossible is part of what makes the Bootes void interesting. It pushes researchers to explore the limits of their models without breaking them. The next question concerns density. It's one thing for a void to be large. It's another for it to be so empty. If large voids merge, their combined emptiness might deepen. Surrounding matter gets pulled into nearby filaments and walls, leaving behind a region even more sparse than before. The Bootes void's internal galaxies, few as they are, likely represent the remnants of matter that didn't get pulled outward. These galaxies are interesting because their isolation shows how extreme the void's conditions are. Galaxies inside such a region don't experience the typical interactions that influence star formation, galaxy shape, or merger history. They're like small towns located far from large cities, growing at their own steady pace. The idea of a bubble too big to make sense of also extends to how the void influences its surroundings. Any region of space that large has subtle gravitational effects. Even emptiness has consequences. The Bootes void doesn't pull matter inward like a cluster would, but its absence of matter creates a kind of contrast that shapes the edges of surrounding structures. The filaments that border the void become more defined because the difference between dense and empty regions is sharper. This enhanced contrast exaggerates the patterns around the void, making the cosmic web appear even more structured. Think of it like stretching a sheet of fabric with a large hollow underneath. The edges of the hollow become more pronounced as the sheet sags into the empty space. In a similar way, the Bootes void sharpens the structure around it, giving astronomers a clearer view of how matter behaves on large scales. But even with all these insights, the initial reaction of many researchers was still anchored in that sense of disproportion. Voids were expected, but not on this magnitude. It's common for scientists to feel uneasy when something defies everyday intuition, even when it fits into the broader framework of theory. The Bootes void didn't break the rules, but it bent expectations far enough that it demanded a careful look. Another way to grasp its size is to compare it to familiar cosmic distances. The Milky Way is about 100,000 light-years across. The entire local group, which includes the Milky Way, Andromeda, and dozens of smaller galaxies, spans a few million light-years. Beyond that, galaxy clusters can be tens of millions of light-years wide. But the Boots void dwarfs all of these. It's not just larger, it's larger by orders of magnitude. This kind of comparison helps make the size feel more grounded. When people hear 300 million light-years, the number is abstract. But when you compare it to the scale of our own galaxy, or even our galaxy cluster, the difference becomes more concrete. The feeling that the void is too big to make sense of also stems from how rarely such extreme structures appear in simulations. They appear, but not often. Their rarity makes them valuable for testing theories. If the universe contains several unusually large voids, then models may need adjustment. But if these voids are spaced far apart in both time and distance, they may simply be statistical outliers. Just like rare weather events occur on Earth, rare structures occur in the universe. They're unusual, but they don't violate natural laws. Astronomers need structures like the Boots void to challenge their understanding. Without rare cases, models can become too comfortable. Extreme examples help ensure that theories can handle the full range of possibilities. In this way, the void becomes more than an oddity. It becomes a tool, something that pushes scientists to refine their assumptions about matter distribution, gravitational dynamics, and cosmic history. Another aspect that made the void surprising was its shape. Many large voids have irregular boundaries. They stretch unevenly. Their edges vary in thickness. But the Bootes void is closer to spherical than most. This near-spherical shape suggests a long, smooth expansion. It implies that the void grew gradually in all directions, rather than being stretched disproportionately by neighbouring structures. That uniformity is unusual because the cosmic web typically influences voids in uneven ways. Gravity pulls matter into nearby filaments, and those filaments tug on neighbouring voids. This can deform the void's shape, making it more elongated or irregular. The Bootes void's shape suggests a more balanced environment. It may have formed far enough from major filaments that its expansion remained even. That raises questions about its initial placement in the early universe. If it began as a region of lower density surrounded by relatively uniform space, it could have expanded evenly over time. But even that scenario requires conditions that aren't extremely common. Despite all these factors, the void remains something that models can account for. It sits at the outer limits of what simulations predict, but it doesn't break those predictions. This is part of why astronomers describe it as remarkable rather than impossible. It is one of the largest voids discovered, but not a contradiction. It challenges expectations, but it does not violate established physics. One of the lingering questions about the Bootes void is whether it represents a unique environment for galaxy evolution. The galaxies inside it likely had fewer interactions over time. They experienced less gravitational harassment from neighbours. They may have formed fewer new stars due to limited gas inflow. Their isolation makes them valuable case studies. Understanding how galaxies behave in low-density regions helps scientists compare them with galaxies in clusters, groups, and filaments. These comparisons help uncover the influence of environment on galaxy development. The void's existence also raises questions about dark matter distribution. Dark matter affects how galaxies move and cluster. If the void has less dark matter than surrounding regions, that could explain why fewer galaxies formed there. Studying the void's gravitational effects helps researchers map dark matter indirectly, even though it cannot be seen directly. The Bootes void, therefore, becomes a laboratory for studying the relationship between visible matter and dark matter on large scales. Even though the void is enormous and surprising, the more astronomers study it, the more it becomes part of the broader understanding of cosmic structure. It remains special, but not inexplicable. It reminds researchers that the universe is not perfectly uniform, and that rare, extreme structures can and do occur. These structures add depth and complexity to the cosmic web. As astronomers continued examining the void, they became increasingly interested in the boundaries where the empty region meets the denser filaments. These boundaries hold clues about how matter flows over time. They show how galaxies form clusters along edges, leaving the interior open. They also show where gravity has been strongest and where material collected. Studying these transitions helps refine theories of structure formation and gives insight into the universe's early conditions. When astronomers finally came to terms with the size of the Bootes void, the natural next step was to imagine what it would be like inside it. Not from the outside looking in, where you see numbers on a map or density charts on a screen, but from the inside looking out, as if you were drifting through it. Trying to picture that experience forces you to confront just how unusual the Bootes void really is. Space is always sparse compared to the standards we know on Earth, but the Bootes void takes that sparseness to another scale entirely. It becomes something like a dark desert of galaxies, a region where the familiar markers of the universe become spread so thin that the sense of scale begins to distort. When astronomers use the phrase dark desert, they are not trying to sound dramatic. They are describing a place where there are so few galaxies that the view would be profoundly different from anything near our part of the cosmos. If you live inside a typical galaxy cluster or even in a quieter galactic neighbourhood, the night sky contains a mix of local stars and distant galaxies. Even though our eyes cannot see most of those faraway galaxies, instruments reveal an environment filled with faint glimmers and signals. But inside the Bootes void, those glimmers would be rare, faint, and spaced incredibly far apart. The region contains only a few dozen galaxies scattered across a volume so enormous that even if you travelled at the speed of light, you could journey for tens of millions of years without passing near one. To understand how empty this space truly is, imagine standing at the edge of a field at night. If it's winter, the trees may be bare. If it's quiet, the air might feel still. But no matter how vast the field, you still have boundaries. The trees, the hills in the distance, the feeling of air moving around you. Now imagine taking away every boundary. No trees, no hills, no sound, no air. Imagine stretching that experience to a scale so large that your mind stops trying to measure it. That's what the interior of the Bootes void would be like. Not a field, but an expanse where the distances between galaxies become so large that normal concepts of proximity no longer apply. It helps to consider the distances involved. In the typical cosmic environment around the Milky Way, galaxies are separated by a few million light years. That is already an immense distance. But inside the Bootes void, the separation between galaxies can stretch to tens of millions of light years or more. It is not simply a larger version of the space between typical galaxies. It is a scale where the emptiness becomes the dominant feature. A single galaxy inside the void would be like a settlement in the middle of a vast silent plain, with no nearby neighbours to interact with for an unimaginable length of time. This isolation has consequences for how galaxies inside the void behave. Galaxies evolve through interactions. They collide, merge, trade gas, distort each other gravitationally, and exchange material over time. These interactions are part of why galaxies develop the shapes and structures they have. Spiral arms, central bulges, and star-forming regions all owe something to these exchanges. In a void, those interactions happen far less often. A galaxy inside the Bootes void would experience fewer external influences, fewer gravitational pulls, fewer close encounters. Over billions of years, this isolation shapes its evolution. Some may remain small and quiet, forming stars slowly. Others may drift along without changing much at all. It also means that if you were inside one of these galaxies and looked out at the universe, your view would be dramatically limited. The night sky would be dominated by the stars of your own galaxy, but the view beyond that would contain far fewer distant galaxies. You wouldn't see the same crowded backdrop that astronomers on Earth detect with telescopes. You would look outward and find long stretches of apparent darkness. Only occasionally would a faint smudge from a distant galaxy show up. That smudge might be millions of times fainter than what we see from Earth when we look at nearby galaxies in dense regions. This difference in perspective is important because it highlights how limited human perception is. We assume our view is typical because it is the only one we know. But the universe is not uniform in how it presents itself. A civilization living inside the Bootes void would likely develop a very different picture of cosmic structure. They might conclude that the universe is sparsely populated, with only a few galaxies scattered across space. They might not suspect the existence of dense clusters or elaborate filaments until they developed instruments capable of seeing far beyond their local region. Their first impression of the universe would be shaped by the emptiness around them. That kind of thought experiment helps explain why astronomers find the Bootes void so fascinating. It's not just an empty region. It is a place where the usual rules of perception change. It makes you rethink what it means to observe the universe. When you stand on Earth and look outward, you see a universe shaped by the environment we live in. If your galaxy were instead inside the Bootes void, the universe would look like a very different place. The Bootes void acts like a natural experiment in perception, showing that the structure of the universe affects how any observer anywhere might interpret it. The emptiness also creates a sense of scale that is almost impossible to grasp. Even astronomers who work with these numbers daily still treat the Bootes void with a sense of caution, because the human brain isn't built for distances measured in hundreds of millions of light years. When someone describes a distance of 10 million light years, the number becomes an abstraction. When someone describes a region nearly 300 million light years wide, the abstraction becomes even more extreme. To put that into perspective, the void is so large that if the Milky Way were at its centre, the nearest galaxies outside the void would be far beyond the range of even the most distant objects we can see with the naked eye. Our sky would look strangely incomplete. The void's interior also raises questions about how galaxies form in such environments. The galaxies inside it are often studied for their unusual features. Since they are isolated, their shapes and behaviours can reveal how galaxies evolve without external pressures. Some void galaxies are small and faint. Others appear surprisingly normal. A few show evidence of slow but steady star formation. These galaxies help astronomers understand how environment affects evolution. In dense clusters, galaxies are constantly interacting. In voids, galaxies evolve quietly. Comparing the two groups reveals important differences in how stars form, how gas behaves, and how dark matter influences structure. Another question that arises when staring into the emptiness is how such a region remains so empty. Over billions of years, matter tends to drift into denser regions due to gravity. This process leaves voids behind. But the Bootes void must have started with unusually low density for it to become this large. This suggests it might have expanded faster than the surrounding filaments. When the universe was young, small density differences became the seeds for larger structures. The Bootes void likely formed from one of the lowest density seeds. Gravity could not gather much material there, so as the universe expanded, the region remained underpopulated. But even with these explanations, the void remains a place that stretches imagination. Scientists have mapped it, measured it, and studied the galaxies inside it, but imagining the experience of drifting through it still feels unfamiliar. If you picture yourself travelling across the universe, the Bootes void is one of the few places where the scenery would remain almost unchanged for an inconceivably long time. You could travel across distances that would normally reveal new galaxies every few million light years. But inside the void, you might see nothing but darkness ahead, with only the faint glow of your originating galaxy behind you. This kind of environment challenges common assumptions about exploration. People often imagine space travel as passing by stars, nebulae or clusters, but real intergalactic space is mostly empty, and a void like Bootes magnifies that emptiness. Light becomes rare, landmarks become scarce. The typical points of reference that help orient travellers simply do not exist. Navigation would depend almost entirely on instruments. Even with powerful sensors, the distances between galaxies would be so vast that the view outside a spacecraft would remain unchanged for millions of years. Some researchers have compared travelling through a void to drifting in an ocean with no islands in sight, but even that analogy falls short. On Earth, an ocean still contains waves, currents, clouds, and the movement of the atmosphere. In the Buddha's void, there are no waves, no air, no distinguishing features. It is emptiness in the literal sense. The closest analogy might be drifting through calm, unbounded water where visibility extends forever, except that in the void, visibility extends into near total darkness. Another striking element of the void is how invisible it becomes without mapping. To the human eye, space always looks dark, whether you're looking at a dense region or a void. The difference only becomes clear with careful measurement. The Buddha's void does not appear darker than other regions. It doesn't cast a shadow or create a visual absence. But when astronomers map where galaxies are located and build three-dimensional diagrams, the difference leaps out. The void becomes an empty sphere surrounded by walls of galaxies. It turns from invisible to obvious. This also means that staring into the void from Earth doesn't feel any different than staring toward any other patch of sky. The Buddhist void does not stand out in photographs taken with regular cameras or by amateur astronomers. It requires large-scale redshift surveys to reveal. That hidden nature makes it even more interesting. Something so massive, so empty, and so unusual sits quietly behind a familiar set of stars, unnoticed without the right tools. Inside the void, time would also have a different feel. Not because time itself changes, but because change would happen slowly. Galaxies in dense regions often undergo collisions and mergers that dramatically alter their structure. Inside the Buddha's void, such events are rare. A galaxy could drift for billions of years without encountering anything significant. Change happens, but at a pace driven mostly by internal processes rather than external ones. For astronomers studying galaxy evolution, this offers a kind of baseline. It shows what happens when a galaxy grows without constant disruption. This calm environment might mean that void galaxies preserve some early characteristics that galaxies in crowded regions have long since lost. They might contain older stars or retain gas in ways that differ from typical galaxies. They may have avoided the stripping and compression that happen in clusters. All these factors make void galaxies valuable for comparison. They offer insight into what galaxies would look like if they evolved in relative isolation. Another factor that deepens the idea of the Buddha's void as a desert is its effect on how matter moves around it. While galaxies cluster along filaments, matter inside the void moves outward as the void expands. This outflow is subtle but measurable. It shows that voids are not static. They grow over time, becoming larger as surrounding matter flows toward denser regions. This motion helps shape the cosmic web and contributes to the large-scale structure of the universe. Even though the Buddha's void appears empty, it's not entirely featureless. It contains the occasional faint galaxy. It contains gas so thin that it would be nearly impossible to detect. It contains dark matter, though in lower amounts than surrounding areas. All of this contributes to a complex but extremely subtle environment. But compared to normal space, these features are so sparse that they barely influence the overall feel of the void. The dominant feature remains its emptiness. This emptiness encourages astronomers to think about what the early universe must have been like. The Buddha's void represents one extreme of the distribution of matter. By studying this extreme, scientists can refine their models of how matter initially clumped together. It also helps them test theories of cosmic inflation and the growth of structure. If a region of this size can form naturally, it supports the idea that small initial fluctuations can lead to large differences over billions of years. Another important aspect of staring into the void is realizing that the boundary between emptiness and structure is not abrupt. The transition from a typical galaxy-rich region into the void happens over large distances. Galaxies gradually become less common as you approach the center. It's similar to walking from a densely forested area into a grassland. The change isn't immediate, it happens slowly. Trees become sparse, then fewer, then widely spaced, until finally you reach an open area. The Buddha's void follows a similar pattern. The outer regions contain some galaxies. As you move inward, the density drops steadily. That gradual transition makes the void feel more realistic and less like an artificial hole. It shows how structure naturally forms in the universe. There is no boundary wall or sudden drop-off. Instead, there is a smooth gradient from clustered matter to sparse matter. This gradient helps confirm that the void formed through natural processes rather than through some unusual event. Considering all of this, staring into the interior of the Boots void is not simply imagining an empty region. It is imagining a place where the rules of cosmic neighbourhood change, where distance has a different meaning, where the sense of isolation reaches a level that is difficult to imagine, where galaxies drift in a calm environment, shaped mostly by their own internal processes, where change is slow and interactions are rare. How do you measure something that is mostly nothing? Observational astronomy is built on collecting light. Telescopes gather photons, detectors capture faint signals, and researchers turn those signals into maps. Everything we know about the universe is based on light arriving from somewhere. But a void isn't defined by what lights it up. It's defined by the absence of that light. It's defined by the lack of galaxies, stars, and bright structures. Yet, despite this, astronomers somehow had to figure out the shape, size, and depth of an enormous region where the main feature was emptiness. Measuring nothing is not simple, but it becomes possible when you start by measuring everything around it. Astronomers don't detect the Bootes void by looking for a dark shape. Instead, they detect it by looking for places where galaxies should be, but aren't. This approach requires more than glancing at an image. It requires building a three-dimensional map of galaxy positions, distances, and redshifts. Only when that map is complete enough does the emptiness stand out. If you imagine the cosmos as a giant grid filled with dots, the void appears when one of those sections has far fewer marks than the rest. The first step in building such maps involves cataloguing galaxies. Surveys scan large sections of the sky and record the position of every galaxy visible through the telescope's sensors. Modern surveys can capture hundreds of thousands of galaxies in one sweep. Older surveys captured fewer, but the fundamental idea has always been the same. Each galaxy is a dot in a vast diagram, but a map of dots on a flat surface is only the beginning. Astronomers also need to know how far away each galaxy is. That distance is what turns a two-dimensional diagram into a three-dimensional structure. Distance in astronomy is not measured with a ruler, of course. It's measured using redshift, which tells researchers how much the wavelength of the galaxy's light has stretched as the universe expands. The more the light is stretched, the farther away the galaxy is. This technique allows astronomers to place each galaxy at a specific point inside a virtual space. Over time, these points form a map that extends across hundreds of millions of light years. When the points cluster together, astronomers see filaments and walls. When the points thin out, astronomers see voids. For the Bootes void, this approach revealed a space where very few points existed. Instead of a dense pattern, the map showed a hollow region. That was the first step in measuring the void, mapping what was present. Only by seeing the crowded regions does the contrast become obvious. Without the surrounding galaxies, the void would not stand out. It is the structure around it that defines the emptiness. But even once the gap became apparent, astronomers still had to determine its boundaries. A void is not a perfect sphere. It isn't carved neatly. It has gradients where galactic density slowly decreases before dropping to its minimum. Picking the exact edges requires systematic decision-making. Astronomers define a void as a region where the density of galaxies falls far below the cosmic average. But deciding exactly where far below begins is open to interpretation. If you draw the line too narrowly, you cut away part of the void. If you draw it too widely, the void blends into surrounding space. This challenge forces researchers to use consistent statistical methods. One common approach is to calculate the average number of galaxies per unit volume in the universe. Then, a void is identified as a region where the density falls below a certain threshold. For the Bootes void, that threshold becomes strikingly clear. The region contains only a fraction of the galaxies expected for its size. When researchers apply the threshold formula, the void jumps out as one of the most extreme underdense regions ever measured. From here, astronomers calculate the size. They analyse the three-dimensional shape by identifying all the points around the void where galaxy density rises again. These boundary points form a rough shell. That shell can be approximated as a sphere or an ellipsoid. In the case of the Bootes void, the shape is surprisingly close to spherical, but the exact measurement depends on how far you want to stretch the definition. Once the boundary is set, calculating the diameter is straightforward. It becomes a simple matter of measuring the distance across the widest part. That measurement gives the void its nearly 300 million light-year scale. But such a number feels unreal without context. This is why astronomers often compare it to the distances between known galaxies or the size of the Milky Way. These comparisons allow people to recognise how dramatic the void is. But in the raw data, the void is just a gap, a region that lacks dots on a map. The numbers come from counting and measuring those missing dots. Another question arises when measuring nothing. How do you know there isn't something faint hidden inside the void that your instruments missed? This is where deeper observations come in. Once the void was identified, astronomers began pointing more sensitive telescopes toward it. These telescopes could detect fainter galaxies that early surveys missed. As expected, the void was not perfectly empty. A few faint galaxies appeared, but not enough to challenge its classification as an extreme void. In fact, the presence of these rare galaxies helped refine the void structure. They showed where the density hits its lowest point and where slight increases occur. Some of these faint galaxies inside the void are what astronomers call void galaxies. Their properties are studied to understand how isolation affects star formation and galactic evolution. But scientifically, they serve another purpose. They prove that the void isn't simply an observational error. They validate the measurements. If data were missing or flawed, the void would look empty but secretly contain many galaxies. The fact that researchers can detect rare, isolated galaxies shows that the surveys are sufficiently sensitive. The empty regions are genuinely empty. The next step in measuring emptiness involves understanding how matter moves in and around the void. Voids expand. As the universe grows, the emptiest regions grow faster because they have less gravitational pull to counter expansion. By measuring how galaxies at the edges move, astronomers can estimate how rapidly the void is expanding. This motion helps determine the void's overall density profile. More expansion means lower density. That information contributes to models showing how the void formed. Even though there is little matter inside it, the void still influences nearby galaxies. Galaxies at the boundary feel gravitational forces from filaments and clusters. The void itself doesn't pull them inward, but the surrounding walls pull them outward. By studying these flows, astronomers get an indirect measurement of the void's effect on cosmic dynamics. This helps confirm its size and location. It also helps distinguish between the void's central cavity and its outer transition zones. Another approach involves measuring temperature variations in cosmic microwave background radiation. The cosmic microwave background is the afterglow of the early universe. It has tiny fluctuations that can reveal details about matter distribution. When photons from the background pass through a void, they experience slightly different gravitational effects than when passing through dense regions. This subtle shift helps astronomers confirm the existence of large voids. The Bootes void is so large that its imprint on cosmic background radiation can be detected statistically. It is not a dramatic signature, but it contributes to the overall measurement. Sometimes the calculations involve comparing the Bootes void to simulated universes. These simulations model how matter would have moved over billions of years, starting from the conditions of the early universe. If simulated universes produce voids similar in size to Bootes, then the void is consistent with current theory. If the simulations rarely produce such voids, then researchers must refine their parameters. Measuring the emptiness of the Bootes void also means understanding how often such voids should occur. Astronomers run hundreds of simulations to compare the predicted distribution of voids with the Bootes example. In most simulations, voids of this size are rare but not impossible. This statistical approach helps confirm that the void fits within the known laws of physics. Another subtlety arises when measuring emptiness: defining the centre. Voids don't always have a simple central point. The density might be lowest at more than one location, or the shape might be slightly irregular. But for practical purposes, astronomers approximate a centre based on the region of lowest density. That centre becomes a reference point for measuring radial density changes. From there, the void structure becomes clear, sparse in the middle, gradually increasing toward the edges. This gradient gives the void its internal profile. One challenge in all this is that emptiness is not visually dramatic. A galaxy cluster is easy to recognise. A void looks almost identical to any other patch of black sky. But when measured in a three-dimensional map, the void becomes a huge bubble of negative space. The maps reveal a shape carved not out of light, but out of its absence. This representation helps people grasp its existence in a way that the night sky alone cannot. Astronomers also use special software that analyses galaxy distribution automatically. These programs identify voids by calculating where galaxies are missing. The algorithms detect low-density regions and outline their shapes. These tools allow researchers to measure voids consistently across large data sets. When the software was applied to the Bootes region, it produced a large empty bubble. The consistency of these algorithmic measurements reinforces the data from human observation. Some people wonder whether a void might contain hidden objects such as faint gas clouds or dark matter structures that cannot be detected easily. And indeed, voids do contain dark matter, though in much smaller amounts than surrounding regions. But this dark matter still has gravitational effects. By studying the motion of galaxies at the edges, astronomers can estimate how much dark matter the void contains. The Bootes void has significantly less dark matter than average, which confirms its classification as a deep void. This low dark matter density also explains the scarcity of galaxies. Without dark matter, galaxies cannot form easily. Another question that arises is whether other forms of matter or energy might be hidden inside the void. For example, could there be faint gas spread so thin that it escapes detection? Possibly, but the gas would be extremely low density. It would not contribute significantly to galaxy formation, and its presence would not change the classification of the void. The emptiness of the Bootes void is not defined by absolute vacuum, but by relative density. It is empty compared to surrounding regions and compared to average cosmic density. Studying the void also involves looking at its effect on cosmic expansion. Voids act like super-expanding regions. They grow faster than dense areas. By comparing the size of the Bootes void across cosmic time, astronomers can estimate how expansion affects large-scale structure. This measurement helps refine cosmological models. It also helps determine whether voids behave the way theory predicts. So far, the Bootes void fits those predictions. It expands at a rate consistent with models of dark energy and cosmic acceleration. Measuring emptiness also requires long-term data collection. The first maps of the Bootes void were incomplete. Over time, better instruments added more detail. New surveys revealed more galaxies at the edges. High-resolution maps helped refine the shape. Each new survey contributed another layer of measurement. The Bootes void gradually shifted from a surprising gap to a well-characterized structure. But the process took decades. Emptiness does not reveal itself quickly. It requires repeated measurements, incremental improvements, and confirmation from independent data. The techniques used to measure the void have also improved with technology. Early surveys used photographic plates. Later ones used digital detectors. Modern surveys use advanced spectrographs that can measure redshifts for countless galaxies at once. As instruments improve, the picture becomes clearer. But even with the best tools, the void remains a place defined more by what is missing than by what is present. It is also interesting to consider how much measurement relies on perspective. Humans see a dark patch in the sky and assume it looks the same everywhere. But the night sky is only a slice of the universe. Measuring a void means building a three-dimensional view that goes far beyond human vision. The measurement tools become an extension of perception, allowing researchers to see structure that would otherwise remain hidden. The void is not visible to the eye, but it becomes visible through data. Another aspect of measuring voids is confidence. How certain can astronomers be about the measurements? For the Bhutas void, the confidence grows with each new survey. The void's presence has been confirmed by many different methods. Its boundaries have been redrawn with increasing precision. The number of galaxies inside it has been updated as instruments detect fainter objects. The shape and size have been refined with each generation of data. Confidence grows not from a single measurement, but from accumulation. And yet, even with all the data available, the process remains an exercise in interpreting absence. Measuring emptiness requires relying on the structures that surround it, the few galaxies that wander inside it, and the overall motion of matter around it. It requires building a picture from gaps. It means studying what isn't there as much as what is. When astronomers look at the Bhutas void and try to explain why it exists at all, they face a puzzle that is both simple on the surface and complicated underneath. On one level, the explanation seems straightforward. Voids form where matter was sparse in the early universe. Places that began with slightly less material gradually became emptier as surrounding regions drew matter away. Over billions of years, the sparse spots expanded into deep hollows. This logic fits neatly into cosmological theory. Every map of the early universe shows tiny fluctuations in density, and those fluctuations acted like the seeds of all structure. But the Bhutas void does not feel like an ordinary hollow. Its size and depth force researchers to think about those early conditions more carefully. When something is unusually large, even if it fits within theoretical possibilities, it encourages deeper examination. The puzzle begins with the basic question of initial density differences. Just after the Big Bang, the universe was filled with a nearly uniform soup of particles and radiation. The temperature was almost identical everywhere, with tiny variations measured at a scale of 1 part in 100,000. These small imbalances, though nearly invisible, were enough to grow into galaxies, clusters, filaments, and voids. Places with slightly more material became dense over time. Places with slightly less became empty. This simple principle guides most models. But if the Bhutas void grew out of one of these small underdense regions, then the early fluctuation that seeded it must have been significantly lower than average. That, in turn, raises questions about how unusual such a fluctuation would be. If the fluctuation was extremely rare, then the void becomes a statistical outlier. That would not necessarily be a problem. Rare events happen. But if it required too rare a fluctuation, then cosmological models would need to explain why such a region formed at all. When researchers analyse the distribution of density in the early universe, they find that deep underdense regions are possible, but not common. The Bhutas void matches the behaviour of one of these deeper fluctuations, so the puzzle is not that it shouldn't exist. The puzzle is why one formed at this size rather than smaller. Some astronomers approach this by looking at the history of void merging. Smaller voids can merge into large ones over time. If several underdense regions formed near each other in the early universe, they might expand and gradually blend into a single large void. This process smooths out the boundaries and creates a more continuous region of low density. Models show that void merging is common. Many large voids discovered in surveys appear to have formed this way. But for the Bhutas void to reach its enormous size, the initial arrangement of small voids must have been unusually favourable. There must have been a cluster of low-density regions positioned close enough and formed early enough to expand into one another before being disrupted by nearby filaments. Thinking about this is like imagining puddles merging after rain. Most puddles merge into shallow pools, but occasionally a pattern of depressions allows several puddles to join into a larger body of water. The shape of the ground decides how big the merged pool becomes. In the same way, the layout of early density fluctuations affects how voids grow. If the Boots void formed from merging, its growth was likely shaped by the surrounding density landscape. The areas around it must have contained enough matter to prevent collapse, but not so much that they restricted expansion. This balance is delicate and unlikely, but not impossible. Another part of the puzzle involves the relationship between voids and dark matter. Dark matter makes up most of the universe's mass, and its distribution determines where galaxies form. If a region begins with less dark matter, it forms fewer galaxies. If it begins with more, it forms dense clusters. The Bootes void likely contains significantly less dark matter than average. This low dark matter density is one reason so few galaxies exist inside it. Without the gravitational scaffolding provided by dark matter, gas does not collect into stars easily. As a result, the void's existence points back toward a region where dark matter was scarce. The question then becomes how such a region happened to contain so little dark matter compared to neighbouring areas. This leads to a deeper puzzle. Why would dark matter distribute itself unevenly in that way? Most cosmological theories treat dark matter as a nearly uniform substance in the early universe, with fluctuations matching those of normal matter at large scales. But on small scales, differences can occur. Some simulations show that rare, deep underdensities can form spontaneously. Others show that interactions between expanding regions and neighbouring clusters can amplify underdensities. If the Bootes void formed near a region where matter was moving outward rapidly, that motion could have further thinned the region. These dynamics are subtle and require precise modelling to understand. The void becomes a window into how dark matter behaved billions of years ago. There is also a question about timing. Voids grow over time as matter flows toward dense regions. A void that starts small can expand significantly if it remains underdense for long enough. If the Bootes void existed early in the universe and stayed underdense for billions of years, it had ample time to stretch into its enormous present size. This process is natural in expanding space, but the amount of stretching depends on the exact density level. A slightly denser region might not expand enough to become so large, so the Bootes void must have started out among the regions with the lowest density. This early condition plays a major role in explaining why it exists. Another element in the puzzle is symmetry. The Bootes void is roughly spherical, which is unusual for a void of its size. Many voids have irregular shapes because the surrounding structures exert uneven gravitational forces. Filaments and clusters tug on voids differently depending on where they sit. This uneven tugging stretches voids in one direction, flattens them in another, and gives them complex shapes. The Bootes void, however, appears relatively balanced. Its boundaries curve evenly in all directions. This symmetry suggests that the void grew in an environment with relatively few strong distortions. It may have been surrounded by structures that, while dense, were evenly distributed enough to allow smooth expansion. This raises an interesting line of thought. If the void grew evenly, then its surroundings must have been arranged in a way that did not significantly deform it. That arrangement itself is unusual because the universe's large-scale structure is not symmetrical. Filaments branch out in different directions, meet at nodes, and form complex networks. Voids are the spaces between these networks. For a void to maintain a spherical shape, its neighbours would need to be arranged in a somewhat balanced pattern. This does not require perfect symmetry, but it requires enough uniformity to avoid major distortions. The Bootes void shape suggests that its formation was influenced by an unusually smooth density field. Another part of the puzzle concerns how galaxies inside the void formed. If the region started with very low density, it's reasonable to ask how any galaxies formed at all. The galaxies now found inside the void are few and scattered. Some may have formed from small pockets of matter that survived the early expansion. Others may have drifted into the void over time from surrounding regions. Galaxies move relative to each other over billions of years. Some may have entered the void slowly, carried by the motion of surrounding structures. Studying these galaxies helps astronomers infer how the void evolved. Their properties, age, shape, star formation rate, offer clues about whether they formed in isolation or arrived later. Research shows that many void galaxies are smaller than average. They tend to have simpler structures. They sometimes show signs of ongoing star formation at modest rates. These features support the idea that the void has remained a gentle environment for billions of years. Galaxies here are not subjected to the intense forces present in clusters. They are not stripped of gas. They are not disrupted by repeated collisions. Their quiet evolution supports the notion that the void has existed for most of cosmic history. Another dimension of the puzzle is whether the void has influenced the development of its surroundings. Voids play a role in shaping the cosmic web. Their expansion can affect how filaments grow and stretch. If the Bootes void expanded rapidly in the past, it may have pushed neighbouring filaments outward. This gentle outward pressure does not involve a physical push, but rather the way dark matter flows under gravity. Voids are areas of low gravitational attraction. As they expand, they redirect matter toward denser areas. The Bootes void may have helped determine how nearby structures formed. Understanding this influence is part of solving the puzzle of its existence. Another interesting question is whether other voids like Bootes exist but remain partially hidden. Large voids require extensive surveys to detect. Some voids might overlap with areas of the sky that have been less thoroughly mapped. Others may lie behind regions where observation is difficult due to foreground objects. If more voids of similar size exist, they could help researchers understand whether the Bootes void is truly unusual or simply one example among many. As surveys improve, more large voids have indeed been found, but few match Bootes in both size and emptiness. This suggests that Bootes is at the extreme end of the distribution. The puzzle also touches on the expansion of the universe itself. If the universe expands at an accelerating rate, as current observations suggest, voids become more pronounced over time. Dense regions hold together due to gravity, but empty regions expand more freely. The Bootes void may be a magnified result of this phenomenon. Its early low-density seed combined with accelerated expansion could naturally create a large void. In this view, the void is a natural outcome of cosmic acceleration. Testing this idea requires comparing the void's growth rate with predictions from cosmological models. So far, the void appears to grow consistently with those predictions. Some researchers also consider rare events in the early universe. Extreme density fluctuations could arise from quantum variations during inflation, the rapid expansion that occurred fractions of a second after the Big Bang. These fluctuations were amplified by inflation, producing regions with slightly more or less matter. If the Bootes void came from one of the deeper dips in this early distribution, it would represent a particularly amplified fluctuation. This explanation fits within standard theory, but requires a rare initial condition. The puzzle then becomes one of probability. How rare is rare? And how likely is it that we would find such a void in our observable universe? Another layer of the puzzle involves the BAO, or baryon acoustic oscillations, which describe how sound waves move through the early universe's plasma. These waves created patterns in matter distribution. If the Bootes void sits in a region where these waves interacted in an unusual way, it might have developed differently. Researchers examine these patterns to see whether the void aligns with predicted fluctuations. So far, the void fits within the expected framework, but it remains one of the strongest examples of a low-density region. Even though many explanations exist, the Bootes void remains puzzling because each explanation raises further questions. If it formed from merging voids, why were so many small voids located so close together? If it originated from a deep early fluctuation, what sets that fluctuation apart from others? If its environment shaped its spherical form, why was the surrounding density so evenly arranged? If it reflects natural cosmic expansion, why does it stand out among other voids? Each answer fits, but each answer also invites more investigation. This is part of why astronomers find voids so compelling. They test the limits of models. They represent the thin regions between filaments where many assumptions break down. They emphasize that emptiness is as important to cosmic structure as density. They remind researchers that the universe is shaped just as much by what is missing as by what exists. And as the understanding of the Bootes void continues to grow, the next natural question becomes how this emptiness fits into the broader architecture of the cosmic web, and what its existence tells us about the delicate balance between dense structures and the vast quiet spaces between them. When scientists talk about the structure of the universe, they often describe it as having an odd architecture. Not odd in the sense of being flawed or chaotic, but odd in the sense that it doesn't resemble anything familiar from everyday life. When you look at the arrangement of galaxies from a cosmic perspective, you don't see a smooth spread of stars or a uniform pattern. You see something far stranger. You see filaments stretching across unimaginable distances. You see clusters forming knots where filaments meet. You see walls of galaxies lining the boundaries of vast empty regions. And you see voids like the Bootes void taking up huge volumes with hardly anything inside them. This unusual architecture emerges from the interplay between gravity and expansion, two forces that shape the universe in opposite ways. Gravity pulls matter together. Expansion pulls matter apart. The result of that competition is the cosmic web. To understand how this structure formed, you need to imagine the universe in its earliest moments. Right after the Big Bang, everything was extremely hot, dense, and almost perfectly uniform. There were no galaxies, no stars, no clusters, no voids. The matter in the universe was distributed so evenly that if you zoomed in to look for differences, you would have found only tiny variations in density. These variations were so small that they were nearly indistinguishable, and yet those tiny differences became the foundation of everything that would later form. Gravity amplified them. Regions with slightly more matter pulled in even more. Regions with slightly less matter continued thinning out. Over billions of years, those small fluctuations grew into the structures we see today. This process sounds simple when stated that way, but the outcome is complicated because gravity and expansion act on matter simultaneously. Gravity is always pulling inward, trying to draw material into dense clumps. Expansion is always stretching space outward, trying to spread material apart. The balance between these two forces determines how galaxies form, how clusters grow, and how voids widen. The Bootes void is a clear example of how this balance can produce extreme results. Gravity works slowly on cosmic scales. It doesn't pull everything together instantly. Instead, it acts over millions and billions of years, gradually shaping matter into coherent structures. If you took a region of the early universe that was slightly denser than average, gravity would slowly draw more matter into it. Over time, that region would evolve into a filament, wall, or cluster. These structures then become even stronger gravitational anchors, pulling in nearby material and growing larger. Because these regions become denser, they expand more slowly. The gravitational pull counteracts the outward expansion of space. In some cases, gravity pulls so strongly that the expansion is overcome entirely, causing galaxies to collapse toward one another and form massive clusters. The opposite happens in underdense regions. When an area begins with slightly less matter, it doesn't have enough gravitational pull to resist expansion. As space stretches, the matter inside the region becomes even more spread out. This reduces the gravitational pull further, accelerating the thinning process. Over billions of years, this positive feedback creates voids. The emptiest regions expand faster than dense regions. They widen as the surrounding denser areas pull matter away. The Bootes void is an example of a region where this feedback loop occurred strongly. It began as an underdense region, stayed underdense, and grew into an enormous cavity. This interplay between gravity and expansion explains why the universe looks like a web. Dense regions grow into filaments and clusters. Empty regions inflate into voids. The boundaries between them become incredibly important. Those boundaries are where galaxies collect into walls, forming broad structures that can be hundreds of millions of light years long. These walls help define the shape and size of the voids, but they also show how structured the universe is at large scales. Nothing about this architecture is random. It emerges naturally from the physics that govern how matter behaves under gravity in an expanding space. When researchers examine the cosmic web, they often find that the densest parts and the emptiest parts are linked. The same processes that create voids also create dense filaments. Matter flows from empty regions into dense ones. This flow shapes the entire layout. Visualizing this process requires thinking of the universe as a landscape with hills and valleys. Dense regions are the hills, where matter piles up. Voids are the valleys, where matter has drained away. But unlike a landscape on Earth, this cosmic terrain changes dynamically. The hills grow taller as matter flows in. The valleys grow deeper as matter flows out. This evolving landscape produces the network-like arrangement that defines the universe. One of the most striking features of this architecture is the scale at which it appears. People are accustomed to thinking about galaxies as isolated objects, but galaxies rarely exist in isolation. They are members of groups, clusters, and filaments. Their positions are influenced by the large-scale distribution of matter. The cosmic web spans distances so large that the structures involved dwarf anything within a single galaxy. Clusters can be millions of light-years across. Filaments can stretch for hundreds of millions of light-years. Voids can be even larger. This scale is difficult to imagine, but necessary for making sense of the Bootes void. It is not an anomaly standing alone. It is part of a larger network. Another important piece of this architecture involves dark matter. Without dark matter, the cosmic web would not form the way it does. Dark matter provides the gravitational scaffolding for all large-scale structures. It makes up most of the universe's mass. It clumps together early, forming the first gravitational wells where ordinary matter later falls. As dark matter collapses into filaments and clusters, ordinary matter follows. This is why galaxies form where dark matter is densest. It also explains why voids are so empty. They contain much less dark matter. Without dark matter's gravitational influence, galaxies cannot form easily. The Bootes void likely contains far less dark matter than its surroundings, which helps explain why it has so few galaxies. Expansion plays an equally crucial role. The expansion of the universe stretches space itself. When space stretches, distances between galaxies increase. This stretching affects dense and empty regions differently. Dense regions resist expansion due to gravity. Empty regions expand more freely. This difference is one of the reasons voids grow larger over time. It also means that the contrast between dense regions and empty regions becomes more pronounced as the universe ages. Early in cosmic history, voids were smaller and less defined. Over time, expansion sharpened these differences, creating the strong structure we see today. The Bootes void is one of the clearest examples of how expansion and gravity combine to produce extreme features. It lies in a region where expansion dominated gravity. That domination stretched the region into an enormous cavity. Meanwhile, dense regions around it resisted expansion and formed sharp boundaries. The result is a void that stands out dramatically when mapped. It is as if the universe sculpted a bubble by letting one region expand faster than its neighbours. A natural question arises when looking at this architecture. Why does the cosmic web have a specific scale? Why are filaments and voids hundreds of millions of light-years across instead of much smaller or much larger? The answer lies in the early fluctuations and how gravity amplified them. The scale of the web reflects the scale of those early density variations. Patterns in the cosmic microwave background radiation show the size of these initial fluctuations. Over billions of years, those fluctuations grew into structures of specific scales. Voids reached sizes determined by how the original density dips expanded under cosmic acceleration. The Bootes void sits near the higher end of the expected size range, but it still fits within the limits set by early fluctuations. Another curiosity in the universe's architecture is the presence of superclusters and walls. These are enormous structures that form the densest parts of the web. They appear as long sheets or tightly packed regions filled with galaxies. The Bootes void is bounded by such structures. One side is framed by the Hercules supercluster, another by parts of the Coma cluster region. These dense walls create the impression of the void being enclosed by bright, crowded neighbourhoods. The contrast between these busy boundaries and the empty interior highlights how sharply the cosmic web divides space. Gravity inside these dense regions behaves differently than in the void. Clusters contain hundreds or thousands of galaxies held together by gravity. They show chaotic motions, frequent mergers, and strong gravitational interactions. These busy regions act as hubs in the cosmic web. The voids act as the spaces between those hubs. The interplay between these two environments is essential for understanding the architecture. Each shapes the other. Filaments feed clusters. Voids feed filaments. The entire system works as a dynamic network. The oddness of this architecture becomes even clearer when comparing it to structures on Earth. Nothing in everyday life resembles the cosmic web. Buildings form grids. Natural features form landscapes. Even complex systems like ecosystems or weather patterns do not form structures spanning millions of light years. The scale alone makes the comparison impossible. But more importantly, the processes shaping the cosmic web are unlike anything on Earth. Gravity and expansion operate over distances so large and timescales so long that they create forms that are unfamiliar to human intuition. Despite this, the cosmic web follows simple rules. Areas with more matter pull in more matter. Areas with less matter lose what little they have. This imbalance drives the evolution of the entire universe. The Bootes void highlights the extremes of that imbalance. It shows what happens when a region starts out significantly less dense. It grows into an enormous bubble. Meanwhile, neighbouring regions with more matter grow denser and form intricate structures. Some scientists describe this architecture as self-organising. It does not require direction or design. It emerges naturally from the physical laws governing matter. The patterns form on their own as the universe evolves. This self-organisation helps explain why the cosmic web looks similar across different scales. Large voids resemble smaller voids. Large filaments resemble smaller filaments. The same processes operate everywhere, just at different magnitudes. The oddness of this architecture becomes even more apparent when thinking about how light travels through it. Light travels freely through voids. It encounters far fewer obstacles. In dense regions, light must navigate gas, dust, stars, and galaxies. This difference affects how astronomers observe the universe. Voids can act as windows, offering clear views of distant objects. Dense regions can act as gravitational lenses, bending light paths. Studying light as it moves through different parts of the web reveals the underlying structure. When researchers map the Bootes void, they are not just mapping emptiness. They're also mapping how that emptiness affects the flow of matter and light. The void's growth influences nearby filaments. Its boundaries mark areas where galaxy density increases sharply. These relationships help define the void more precisely. Another aspect of the universe's architecture involves the role of dark energy. Dark energy drives the accelerated expansion of the universe. This acceleration affects the evolution of voids and filaments differently. Voids expand faster because dark energy dominates where matter is scarce. Dense regions resist because gravity counteracts dark energy more effectively. Over time, This difference creates sharper contrasts. The Bootes void reflects this accelerated expansion clearly. Its size is partly a result of dark energy's influence. Even though this architecture may seem strange, it is remarkably consistent. Simulations of the universe, when run with the known laws of physics, produce similar structures. They show filaments, clusters, and voids. They show patterns that closely match what astronomers observe. These simulations validate the underlying theories. They show that the cosmic web is a natural outcome of gravity and expansion, acting on initial fluctuations. The Bootes void remains one of the standout features of this architecture. Because it illustrates the far end of the spectrum, it is one of the deepest voids, one of the largest, one of the most striking examples of how emptiness can become a major component of cosmic structure. But it is still part of the pattern. It is unusual in size, but not beyond explanation. It belongs to the same family as smaller voids. It simply grew more, and as gravity and expansion continue shaping the universe, the Bootes void will continue to evolve slowly. Its boundaries will shift. Its galaxies will drift. Matter will keep flowing out of it into denser regions. Over billions of years, it may grow even larger. Understanding its place in this architecture helps researchers understand the broader structure of the cosmos. If you could step back far enough to view the void and its surroundings as a whole, you would see that it sits inside a sprawling cosmic neighbourhood that looks both familiar and strange at the same time. Familiar because it still contains filaments, clusters, and walls of galaxies, the same kinds of structures found throughout the universe. Strange because these structures line the edges of an enormous cavity, forming an arrangement that seems almost lopsided. The void dominates the region so thoroughly that everything around it looks shaped by its presence. It helps to imagine this neighbourhood as a wide basin in the cosmic web. The edges of the basin are lined with bright structures. The interior is overwhelmingly empty. To understand what this basin looks like, you need to picture the way galaxies cluster in the universe. They don't spread out evenly. They gather along filaments stretching into long strands that connect distant regions. These filaments form boundaries between voids. In the case of the Bootes void, several filaments, clusters, and walls surround it, marking its edges. One of the first things astronomers noticed when mapping the region was how sharply the galaxy density increases at the void's boundary. As you move outward from the centre of the void, the number of galaxies increases slowly at first, then more quickly. Eventually you reach areas with typical or even above average galaxy density. This gradient shows how the void transitions into the rest of the cosmic web. But it also reveals another important detail. The Bootes void is not isolated. It is connected to the larger structure through these boundary regions. Take the Hercules supercluster, for example. This massive cluster lies near one edge of the void. It contains thousands of galaxies, each shaped by billions of years of gravitational interactions. When astronomers map the region, the Hercules supercluster stands out as one of the most prominent features around the void. The contrast between its busy interior and the quiet emptiness of the void is striking. On one side, galaxies collide, merge, and evolve. On the other side, galaxies drift alone in near silence. This sharp contrast helps define the void's boundary. Another nearby structure is the Coma cluster region, part of the Coma supercluster. The Coma cluster is known for being extremely dense. It contains thousands of galaxies tightly packed together. It emits strong X-ray radiation from the hot gas between galaxies. It acts as a gravitational powerhouse, pulling matter inward. When viewed on a large-scale map, the Coma region forms a bright wall near the Bootes void, emphasizing the void's emptiness. It is like standing on the edge of a bustling metropolis and staring into an open plain that stretches far beyond the horizon. Between these major structures lie smaller filaments and groups. These filaments function like cosmic highways. They connect clusters to one another, guiding the flow of matter across the universe. Some of these filaments form arcs around the void. Others curve gently, marking the boundaries of smaller neighbouring voids. If you mapped them in 3 dimensions, they would look like delicate threads creating a frame around the vast hollow inside. This arrangement raises interesting questions about how the void interacts with the surrounding structures. Even though a void contains very little matter, its presence affects how nearby matter behaves. The Bootes void, due to its size, exerts a subtle influence on the expansion and flow of material around it. Matter moves along filaments toward dense clusters, but the void creates a kind of gravitational contrast, offering less resistance to expansion. This difference shapes how filaments stretch and how clusters form near the void's edges. The void acts almost like a soft pressure zone in the cosmic web, influencing patterns without directly pulling on them. To understand this better, imagine that the void is like a large clearing in a forest. The forest edges grow where there is more soil and nutrients. The clearing stays open because that region lacks the resources needed to sustain dense growth. Yet the shape of the clearing influences how the trees develop around it. The trees at the edge grow differently from the ones deeper in the forest. The clearing defines the boundary. The Bootes void does something similar on a scale so vast that the numbers lose ordinary meaning. The galaxies near the edge of the void are especially important for studying this dynamic. These galaxies exist where the density transitions from extremely low to moderately dense. Their distribution helps astronomers trace the boundary more precisely. Some of these galaxies show signs of being influenced by nearby clusters. Others show signs of having evolved in quieter conditions close to the void's interior. By analysing their motion, shape, and star formation rates, researchers gain insight into how galaxies behave in transitional environments. One interesting trend comes from observing how galaxies move near void boundaries. Galaxies just outside a void tend to drift outward, away from the void's interior and toward denser regions. This motion reflects how matter flows through the cosmic web. Dense regions pull matter inward. Voids allow matter to move outward more freely. The boundary becomes a dynamic zone where these opposing motions interact. In the Bootes region, this outward flow further empties the void, while feeding the growth of nearby structures. Another important part of the Bootes void's neighbourhood is the presence of smaller voids nearby. Voids are not isolated features. They cluster just like dense regions do. They form a network of empty pockets surrounded by filaments. The Bootes void is the largest in its area, but not the only one. Other smaller voids sit nearby, forming a patchwork of emptiness. These smaller voids likely contributed to the Bootes void's growth, merging with it over billions of years. When astronomers map these connected voids, they see how the Bootes region forms part of a larger hollow region within the cosmic web. Examining this interconnected set of voids helps researchers understand the void's history. It suggests that the Bootes void may not have always been a single structure. It may have started as several underdense regions that gradually merged. This merging process would have created transitional areas where density was low, but not as low as the void's centre. Over time, these regions would have joined more completely, smoothing out density variations and giving the void the large-scale shape it has today. But even with this merging process, the Bootes void remains unusual for how few galaxies it contains. Neighbouring voids have more galaxies. Even large voids elsewhere in the universe often contain more visible structure. The Bootes region's extreme emptiness sets it apart. To understand why, astronomers look at how the void is positioned relative to nearby structures. One possibility is that the surrounding filaments and clusters absorbed more of the matter that might otherwise have remained in the void. If the region was bordered by especially strong gravitational anchors early in history, those anchors could have pulled material away more effectively. The result would be a void with even less matter than typical. Another possibility is that the void lies in a region where early density fluctuations were especially pronounced. If the void began with one of the deepest underdensities, it would naturally become more extreme as the universe expanded. The neighbourhoods around it would reflect this early imbalance. Some filaments might have grown more rapidly, others might have stretched to accommodate the expanding void. In either case, the void's surroundings become part of the explanation for its unusual character. Astronomers also look at the temperature and distribution of intergalactic gas near the void. Even in empty regions, gas exists, though it is incredibly thin. This gas can reveal clues about how the void interacts with nearby structures. For example, gas near the void might show signs of being pulled toward filaments. It might show temperature differences based on how matter is flowing. These observations add more detail to the picture of the void's neighbourhood. Another element worth considering is the gravitational influence of dark matter. Dark matter forms the backbone of the cosmic web. It collects into filaments and clusters far earlier than ordinary matter does. The distribution of dark matter around the Bootes void helps determine the shape of the surrounding structures. If dark matter density is especially high in the nearby filaments, those filaments would pull ordinary matter more strongly, deepening the void. The arrangement of dark matter can be inferred from how galaxies move and cluster. When researchers examine this motion near the Bootes void, they find patterns consistent with strong filaments and significant underdensity in the void itself. These features combine to create a neighbourhood that looks dramatic when mapped. A nearly spherical cavity sits surrounded by walls and strands of galaxies. The contrast is not subtle. Even though the void cannot be seen directly in photographs, the pattern becomes unmistakable in three-dimensional surveys. The void appears like a vast, silent space carved out of the cosmic web, with galaxies clustering tightly at its boundaries. This arrangement makes the Bootes void's surroundings a useful laboratory for studying the cosmic web's formation. By analysing how the void affects nearby structures, astronomers test theories of large-scale evolution. They study how matter flows along filaments. They examine how voids and dense regions interact. They compare these observations with simulations. The Bootes void, because of its size, provides clear signals in these studies. Its influence is easier to measure than that of smaller voids. Another interesting aspect of the void's neighbourhood is the way it highlights the universe's contrasts. On one side, you have dense clusters filled with galaxies, hot gas and dark matter. On the other side, you have a deep void where galaxies are scarce. The transition between these states is gradual but noticeable. It reflects the universe's tendency to amplify extremes. Dense regions grow denser, empty regions grow emptier. This contrast intensifies over time as the universe expands. Understanding this growing contrast is important for models of cosmic evolution. If the Bootes void continues expanding, its boundaries may shift slowly, and the surrounding filaments may stretch further. Dense regions might move slightly as matter flows away from the void. These small changes accumulate over billions of years. Studying them helps astronomers refine predictions about how the cosmic web will evolve in the future. Something else worth noting about the void's surroundings is how they would look to an observer inside the void. If you lived inside one of the few galaxies scattered through the void and looked outward, you might see bright regions in certain directions where the surrounding filaments lie. These bright directions would represent the densest edges of the void. In other directions you might see nothing beyond faint distant glimmers. This uneven distribution of visible structure would shape how an observer understood the universe. Instead of seeing a balanced sky, they would see a sky with more galaxies clustered in some directions and almost none in others. Their view of the universe would be strongly shaped by the void's boundaries. Comparing this perspective to our own helps highlight how location influences perception. Earth sits in a moderately dense part of the cosmic web. We see many galaxies through telescopes because our sky opens onto several filaments. If we lived deep inside the void, our view would be very different. We might not suspect that the universe contained dense regions unless we developed powerful enough instruments. Our understanding of the cosmic web would emerge more slowly. These differences in perspective help show why studying voids is important. They remind researchers that the universe looks different depending on where you are. An observer inside the Bootes void would map the sky and conclude that the universe is sparsely populated. Only deeper observations would reveal the surrounding filaments. This alternate perspective helps astronomers avoid assumptions based solely on our local environment. As they continue to study the Bootes region, astronomers learn more about how voids interact with their surroundings. They analyse the motion of galaxies near the edges. They examine the shape of filaments. They measure the void's expansion. Each observation adds another detail to the picture of how the void fits into the cosmic web. When people first hear that a region as enormous as the Bootes void exists, the next question they usually ask is simple. If it's so empty, what actually lives inside it? The answer turns out to be both modest and interesting. Modest because there is very little inside the void compared to normal cosmic environments. Interesting because what does exist there offers a rare look at how galaxies behave when left almost entirely alone. Life inside a hole in the cosmos is quiet, sparse, and shaped by conditions that barely resemble the ones found in more populated regions. Understanding this environment requires imagining a place where isolation stretches not just across miles or light years, but across tens of millions of light years at a time. The Bootes void contains a few dozen galaxies at most. When astronomers first discovered the void, they expected it to contain almost none. Later surveys revealed these scattered galaxies sitting like faint embers in an otherwise cold environment. When researchers mapped them, the distribution was irregular. Some were closer to the void's centre, others drifted nearer to the boundary. None formed groups the way galaxies commonly do in denser regions. Each one appeared like a small settlement separated from the next, by distances so large that calling them neighbours would be misleading. This arrangement creates an environment that barely resembles the cosmic neighbourhoods most galaxies belong to. Galaxies inside the void are outliers by default. They exist in a region where gravity is weaker, interactions are rare, and matter is scarce. Because of this, their evolution takes a path that differs from the typical route followed by galaxies near filaments or clusters. Most galaxies in the universe experience frequent encounters. They feel gravitational pulls from nearby systems. They collide, they merge. They have their gas stripped by dense environments. They undergo dramatic events that reshape their stars, disks, and dark matter halos. Void galaxies live quieter lives. They evolve mostly through internal processes rather than external pressures. One of the first things astronomers noticed about void galaxies is their size. Many are small, they are often dwarf galaxies. They contain fewer stars than galaxies in dense regions. Their shapes tend to be simpler. Instead of complex whirl patterns or long extended arms, void galaxies often have irregular forms or faint disks. Some show signs of ongoing star formation, others appear old and quiet. This variety shows that even in isolation, galaxies do not all follow the same path. But the overall trend is clear. Without the influence of nearby galaxies, these systems grow slowly and lack the dramatic features common in busier environments. Another interesting characteristic is the colour of these galaxies. Colour reveals information about the age of stars. Blue galaxies contain young stars. Red galaxies contain older ones. Many void galaxies remain blue for much longer than galaxies in dense regions. This suggests that star formation continued quietly over extended periods. The steady trickle of gas within the galaxy can sustain modest star formation without being disrupted. In denser environments, galaxies often run out of gas quickly because interactions strip gas away or use it up rapidly. Void galaxies avoid these pressures. Their slow, steady evolution allows them to continue forming stars on longer timescales. This raises questions about where the gas comes from. If void galaxies are isolated, how do they maintain the supply needed for star formation? The answer lies in the fact that even voids are not truly empty. They contain extremely thin gas spread across enormous distances. This gas might be too faint for direct detection, but it exists. Galaxies inside the void can gather gas slowly over time. They draw it in through their gravitational pull, allowing them to continue forming stars. This process is inefficient, but it can sustain galaxies for long periods. It also explains why void galaxies often appear less processed than galaxies in clusters. They have not undergone rapid transformations driven by external forces. Another question involves dark matter. Galaxies need dark matter halos to form and remain stable. These halos provide the gravitational structure that holds stars and gas together. The void contains less dark matter than its surroundings, but it still contains enough for galaxies to form. The dark matter halos of void galaxies are often smaller and lighter than those in dense regions. This further contributes to their quiet evolution. Smaller halos attract less gas and experience fewer gravitational interactions. The overall effect is a galaxy that evolves slowly, quietly, and independently. Astronomers study void galaxies closely because they help answer fundamental questions about galaxy formation. If these galaxies form in isolation and evolve without major disturbances, they represent something like a baseline. They show what galaxies would look like if left alone. Comparing void galaxies to galaxies in dense clusters provides insight into how environment shapes evolution. Many features once thought to be intrinsic to galaxies, such as certain shapes or colours, turn out to depend heavily on environment. Void galaxies help reveal these dependencies. Isolation also affects how galaxies inside the void move. In dense regions, galaxies orbit around each other, influenced by a web of gravitational forces. Inside the void, galaxies move slowly and freely. Their motions are not constrained by nearby systems. Their trajectories reflect the large-scale expansion of the void itself. This motion helps astronomers measure the void's growth rate. By tracking how void galaxies drift outward relative to surrounding structures, researchers calculate how quickly the void expands. The expansion rate of the Bootes void is one of the factors that confirm its extreme underdensity. Another feature of life inside the void is the complete absence of certain phenomena. In clusters, galaxies frequently merge. These mergers trigger bursts of star formation and reshape galaxies dramatically. Inside the void, mergers are almost non-existent. The distances between galaxies are too large for interactions to occur regularly. A galaxy inside the void might go billions of years without experiencing anything more than a faint gravitational influence from a distant neighbour. This lack of activity shapes the appearance of void galaxies. They often retain their original form longer. Their gas remains more evenly distributed. Their stars form at a steady rate instead of in intense bursts. The emptiness also affects radiation. In dense regions, the intergalactic medium can be heated by powerful sources such as quasars and supernovae. Inside the void, the intergalactic medium remains colder and quieter. This has subtle effects on gas cooling and star formation. A calmer environment makes it easier for gas to cool and collapse, potentially encouraging the formation of small galaxies. But the low density makes it difficult for such galaxies to grow large. Even though the void contains few galaxies, each one becomes precious for research. Astronomers sometimes joke that they treat void galaxies like rare fossils. Each one provides information that is hard to find elsewhere. One galaxy inside the Bootes void, known as Markarian 501, drew attention for its unusual brightness. It sits near the edge of the void rather than at the centre, and it exhibits strong activity in its core. This activity may reflect a past event or unique internal processes. Studying such galaxies helps researchers understand how outliers behave in environments with little external influence. Other void galaxies are significantly quieter. Some appear as faint smudges in survey images. They contain only a few million stars. Their light is weak. Observing them requires sensitive instruments. These faint galaxies help astronomers probe the limits of star formation in isolated environments. They show how galaxies behave when deprived of external triggers such as collisions. They also help answer questions about how small galaxies persist over time. Beyond the galaxies themselves, the void contains other features worth noting, even if they are subtle. The intergalactic gas, though extremely thin, contributes to the void's thermal and chemical history. Studying this gas is difficult, but indirect methods provide clues. For example, The temperature of the gas can be inferred by examining how it affects the light travelling through it. The chemical composition can reveal whether previous generations of stars enrich the void, or whether it remains relatively pristine. Another component inside the void is dark energy. Dark energy permeates all of space and drives the accelerated expansion of the universe. In dense regions, gravity can partially counteract dark energy. Inside voids, dark energy has more influence. This contributes to the void's expansion. Understanding how dark energy behaves inside such a large underdense region helps refine cosmological models. It provides insight into how expansion varies across different environments. Life inside the void, in the sense of physical processes rather than biological life, is slow. Galaxies evolve gradually. Gas moves gently. Stars form at modest rates. Nothing happens quickly. This slow pace offers a contrast to the rapid changes experienced by galaxies and clusters. It emphasizes how environment shapes the timeline of cosmic evolution. Some galaxies undergo dramatic transformations in relatively short spans. Void galaxies drift through billions of years with minimal disruption. This tranquil environment also raises interesting philosophical questions. For example, what would the night sky look like to an observer living inside one of these void galaxies? The stars within the galaxy would still shine, of course, but beyond that, the sky would contain fewer visible galaxies. Only the brightest distant systems would appear. Most directions would show deep blackness. Only certain parts of the sky, those aligned with the void's boundaries, would reveal clusters of distant galaxies. The sky would look uneven. Some directions would hint at cosmic structure. Others would show nothing. This view would shape how an observer understood the universe. From a scientific perspective, imagining such an observer helps highlight the role of perspective in astronomy. Where you live determines what you can see. Earth sits in a region where nearby filaments provide rich backgrounds of galaxies for telescopes to observe. Someone inside the Bootes void would see a much simpler cosmic map. Their first models of the universe might suggest that galaxies are rare. Only after developing sensitive instruments would they discover the nearby filaments. This difference in perspective helps astronomers recognize how their own position influences their understanding. Despite the emptiness, the void is not static. Its galaxies move gradually. Its boundaries shift slowly. Its expansion continues. Tiny amounts of gas fall slowly toward galaxies. Stars form in a quiet, extended rhythm. Over billions of years, this slow motion shapes the void. The Bootes void is not just an empty patch of space. It is an environment with its own rules, rhythms, and patterns. As researchers learn more about what lives inside the void, they also learn more about how the universe evolves when left mostly unperturbed. These quiet environments become comparisons for studying more active regions. They provide clues about which galactic features arise naturally and which arise from interactions. They help clarify how dark matter halos grow, how gas behaves, and how star formation changes under extreme conditions. Could a region so large and so underdense actually shape the fate of the galaxies around it? The idea feels counterintuitive at first because people tend to think of influence in terms of presence, not absence. A galaxy can shape its neighbours because it has mass. A cluster can shape its surroundings because it exerts gravitational pull. A supermassive black hole can shape its environment because it feeds, heats, and disturbs the matter nearby. But a void seems like the opposite of all that. It is defined by what it lacks. It has little mass. It has few galaxies. It contains only thin, quiet gas. And yet, the Bootes void shows that emptiness itself can act as a force, not because it pushes, but because it removes resistance. It becomes a place where expansion wins, where matter drifts away, and where boundaries shift over billions of years. This effect, subtle but widespread, ends up shaping the destiny of galaxies in surprising ways. To understand how this influence works, you have to consider how matter moves through the cosmic web. Everything in the universe is in motion, pulled inward by gravity or carried outward by expansion. Filaments funnel matter toward clusters. Clusters anchor galaxies with strong gravitational wells. Voids stretch open as the universe expands. These movements are slow, but over cosmic time they produce major changes. A galaxy today is not in the same place it was billions of years ago. Its path is determined not just by its local environment, but also by the large-scale structure around it. And in that structure, voids play an important role. A void influences matter by giving it more room to move outward. In regions filled with galaxies, dark matter, and gas, gravity can resist the expansion of space. But inside voids, that resistance is weaker. The Boots void's extreme emptiness allows the surrounding space to stretch more freely. As space expands, the few galaxies inside the void drift apart. But this expansion does not stop at the void's boundaries. It affects the galaxies near the edges as well. Galaxies that lie close to the void feel a subtle outward pull, not because the void pulls them, but because nothing anchors them in place. Meanwhile, the dense regions beyond the boundaries pull them inward. These opposing influences create complex motion patterns. Over billions of years, the galaxies near the edge may shift slowly outward along the gradient where density decreases. This outward drift can affect galaxy evolution in several ways. For example, if a galaxy sits near a void boundary, it might be gently pushed away from its original group due to the surrounding flow of matter. Over long periods, this can lead to isolation, allowing the galaxy to evolve differently from its former neighbours. Instead of merging with nearby systems, it might drift into a quieter region. It might avoid collisions that otherwise would have transformed it. It might retain its gas instead of having it stripped away in interactions. The fate of such a galaxy becomes intertwined with the void's existence. Another way voids influence galaxies is through gas distribution. Gas flows through filaments toward dense regions, but the presence of a large void can alter these flows. Imagine a river feeding multiple channels. If one channel widens significantly, the flow in the surrounding areas changes too. In the universe, voids act like widened channels. They become regions where gas density is low and where flows are redirected. Galaxies near the void's border experience this shift. Their supply of gas may change depending on how gas streams through the region. If a galaxy receives less gas, its star formation slows. If it receives more gas because its trajectory brings it near a filament, its star formation may increase. These long-term changes affect the galaxy's colour, size and structure. Over billions of years, even slight differences in gas supply become significant. The Bootes void contributes to these differences by reshaping the distribution of gas and altering how it flows across large distances. Another subtle effect involves dark matter. Dark matter acts as the framework for the cosmic web. It forms the first structures in the universe and guides the formation of galaxies. Voids contain less dark matter than surrounding regions. This uneven distribution affects how galaxies move. It also affects how galaxies grow. A galaxy near a void boundary might experience weaker gravitational interactions than one near a dense filament. This can slow down the merging process. It can reduce tidal interactions. It can preserve certain features for longer. Conversely, a galaxy being pulled into a filament might grow more quickly due to stronger dark matter influences and increased gravitational stability. All these factors combine to make voids an important element in shaping galaxy evolution. They don't act like clusters, which impose strong direct influence on their members. Instead, voids act indirectly. They influence by making space more flexible. They influence by allowing expansion to dominate. They influence by changing the background environment in which galaxies live. The Bootes void, because of its size, exaggerates these effects. Its presence is large enough to shape the flow of matter on scales of hundreds of millions of light years. Some of the most interesting galaxies to study are those that exist just outside the Bootes void. These galaxies sit in the transition zone between emptiness and structure. Their positions provide clues about how the void influences their evolution. When astronomers measure the motion of these galaxies, they find that many move outward, away from the void's centre. This outward motion is not driven by a push from the void, but by the gravitational pull of nearby clusters. The void contributes by removing competing forces. These galaxies feel more pull from the structures on the opposite side of the void, creating directional motion. This motion can influence which galaxies enter groups and which remain isolated. A galaxy drifting away from the void toward a cluster might join a new gravitational system. Over billions of years, this could determine whether it eventually merges with another galaxy, or remains separate. It could determine whether it grows larger or stays compact. It could determine how much gas it collects and how many stars it forms. In this way, the void indirectly shapes its long-term fate. Another angle to consider is how voids shape the large-scale behaviour of the cosmic web. Voids are not passive gaps. They expand at different rates depending on their density. As they expand, they tug lightly on the surrounding structure. This tug is subtle but widespread. It can change the position of filaments. It can alter the pace at which certain regions grow. It can shift the direction of matter flows. Over time, these influences help sculpt the architecture of the universe. The Bootes void, due to its vast size, contributes noticeably to this large-scale sculpting. At smaller scales, voids can influence the rotation and shape of galaxies. For example, if a galaxy grows near a void's boundary, the lower density environment may affect how its angular momentum evolves. Angular momentum determines how a galaxy spins and how its stars orbit. In dense environments, frequent interactions alter angular momentum constantly. In voids, these changes occur more gradually. The resulting galaxies may have different rotational properties compared to galaxies and clusters. These differences offer clues about how environment shapes galactic structure. There is also the question of how voids affect the development of cosmic flows. Cosmic flows are the large-scale movements of matter driven by gravitational differences. Dense regions pull. Void regions allow matter to move outward. These combined movements create patterns that influence galaxy positions over billions of years. When researchers study the Bootes void, they are not simply examining one hollow space. They are studying one node in a massive system of flows. The void acts like a wide basin into which no matter collects. Instead, matter flows around it, shaping the filaments nearby. This flow pattern may explain why certain nearby clusters formed where they did. Regions around the void might have gained matter more efficiently. Filaments might have thickened due to redirected flows. Clusters may have grown faster due to being fed by these influences. The Bootes void may have helped determine which parts of the cosmic web grew most rapidly and which remained relatively unchanged. This kind of influence demonstrates that even absence can help define presence. Galaxies inside the void experience the opposite effect. They move with the expanding space, drifting farther apart. They slowly lose contact with other galaxies. Even faint gravitational ties dissolve over time. Their fates become lonely, shaped mostly by internal processes rather than by interactions. Some might remain small and gas-rich for billions of years. Others might slowly fade as star formation declines. Their futures remain heavily shaped by the void's emptiness. But galaxies on the edges encounter a different reality. They feel the pull of the crowded regions nearby. They move toward filaments, where interactions increase and evolution accelerates. The void acts as a dividing space between these two modes of evolution, one slow and quiet, the other quicker and more chaotic. Understanding this contrast helps scientists understand the broader range of galaxy behaviours. Another way to think about the void's influence is to consider what would happen if it did not exist. If the Bootes region had formed with average density, the surrounding structures might look very different. Filaments would have had less room to grow outward. Clusters might have pulled in less matter. The flow of gas might have followed different routes. Some galaxies might never have become isolated. Others might never have joined groups. The cosmic web around the Bootes region would likely have a different shape. This thought experiment shows how important voids are to the structure of the universe. Their existence affects everything around them, even though they themselves contain very little. As researchers continue to study cosmic voids, they are discovering that voids may be among the most important environments for testing theories of cosmic expansion. Because voids have so little matter, their expansion depends strongly on dark energy. This makes them natural laboratories for studying how dark energy behaves. If voids expand faster or slower than predictions, it could reveal something new about the universe. The Bootes void, being one of the largest, provides a strong signal for these tests. Its size, shape, and expansion pattern help confirm or refine cosmological models. Galaxies inside voids also serve as indicators of how dark energy shapes cosmic evolution. If dark energy accelerates expansion more strongly in emptier regions, then the internal spacing of void galaxies reveals that behaviour. Studying their motion helps researchers understand how expansion varies across the universe. Even though the Bootes void contains few galaxies, those galaxies provide key data points. The void's influence also extends into how star formation behaves at the edges. Some galaxies experience increased star formation when moving toward denser regions. The change in environment triggers compressions in gas. These compressions can lead to new generations of stars. Other galaxies may have their star formation throttled as they enter denser areas where gas is stripped away. The void, by influencing galaxy motion, helps determine which of these outcomes occurs. Even the chemical evolution of galaxies can be shaped by their position near a void. Galaxies in dense environments can be enriched with heavy elements through repeated interactions. Void galaxies experience fewer such events. Their chemical composition reflects a slower, steadier evolution. Galaxies moving from the void into denser regions show these signatures. Their chemistry becomes evidence of their journey. Studying these differences gives researchers a clearer view of how galaxies evolve, not just as isolated objects, but as members of a dynamic universe shaped by large-scale forces. Void environments become part of that story. The Bootes void becomes an example of how even the quietest parts of the universe participate in shaping cosmic history. As astronomers continue to map the Bootes region and study the galaxies within and around it, they build a more complete picture of how emptiness influences the universe. This understanding reinforces the idea that the cosmic web is not defined only by its filaments and clusters, but also by the vast silent spaces that stretch between them. When people learn about the Bootes void, something curious often happens. The scientific details come first. They learn how large it is. They learn how empty it is. They learn how far it stretches. But once the initial information settles, there's almost always a pause, a moment where the mind steps back from the numbers and tries to imagine what such emptiness really means. It's in that moment that the Bootes void stops being just a cosmic structure and becomes something more personal. It becomes a place that presses on imagination in a way few other things can. A place that forces a person to think about silence on a scale that human instincts are not designed to handle. This reaction is natural because human beings evolved in environments filled with sensory detail. Every moment of daily life contains sound, movement, texture, colour and contact. Even the quietest human spaces have subtle cues that help orient the mind. A distant hum, the feel of air, the presence of gravity, the sense of nearby objects, the awareness of walls, trees, ground or sky. These cues provide reassurance without anyone noticing it consciously. They make emptiness manageable. They prevent silence from becoming overwhelming. But the Bootes void is not a quiet room or an empty field. It is a region where the familiar cues do not exist. It is a place where the idea of emptiness expands far beyond anything the mind evolved to understand. Trying to imagine standing in a galaxy deep inside the void, looking outward into an environment where other galaxies might be tens of millions of light years away, produces an emotional reaction before it produces a rational one. The scale triggers a part of the mind that responds not to science but to vastness itself. This response is not necessarily fear in the dramatic sense. It's something quieter and more subtle. a sense of discomfort that arises from the brain trying to apply instincts meant for short distances to a reality measured across cosmic expanses. Humans instinctively scan environments for threat, support, comfort, and proximity. These instincts are built around immediate surroundings. When the surroundings grow beyond comprehension, the instincts have nothing to grasp. It is like reaching for a railing that isn't there. Even though nothing is physically wrong, the absence of reference points creates a slow, uneasy sensation that sits just beneath awareness. Astronomers feel this too, even though they work with these structures regularly. Many researchers have spoken openly about how imagining the interior of a void can produce a sense of vertigo. Not a physical one, but a cognitive one. A feeling that the mind is momentarily unmoored. They describe the void as something that challenges the brain's expectations, something that makes the usual mental anchors feel insubstantial. And yet, despite this discomfort, astronomers continue studying voids because pushing through that unease reveals something important about how humans relate to the universe. Part of the reaction comes from the fact that voids redefine silence. Silence on Earth is relative. It is the absence of certain sounds, not of all sound. Even in a quiet room, air vibrates, surfaces hum, bodies move. The environment carries faint noises, but inside a void, silence takes on a different meaning. There is no air, there are no surfaces nearby, there is nothing to carry sound. The concept of silence becomes literal. It becomes an environment where the usual signals of life and motion are absent, not just muted. Even imagining that level of quietness can make the mind feel unsettled, because humans rely on sound as one of their key senses for orientation. Another part of the reaction comes from the darkness. On Earth, darkness always contains depth. Even in a pitch-black room, the mind expects something to exist just beyond sight. Darkness hides the environment. It does not remove it. In the Buddha's void, darkness is not hiding anything. It is simply empty space where nothing lies close enough to reflect light. This creates a type of darkness that does not resemble Earth's night. It is a darkness that contains vast distances rather than concealed shapes, and imagining that can make the brain reach for familiar reference points that do not exist. There's also the matter of loneliness in the cosmic sense. People understand loneliness in the context of social contact, emotional connection, and physical presence. But voids present a different kind of loneliness. A galaxy in the Boots void exists in a kind of solitude that is physical, not emotional. It is separated from other galaxies by expanses so large that the usual meaning of nearby stops applying. Thinking about this type of solitude can trigger a quiet, instinctive discomfort because humans naturally compare cosmic distance to emotional distance. Even though galaxies cannot feel loneliness, the mind projects the concept onto them. The emptiness becomes not just physical but symbolic. This projection is similar to what happens when people imagine the deep ocean, the polar regions or deserts. Large empty places on Earth can evoke a sense of awe mixed with unease. The difference is that Earth still offers boundaries and forms. The ocean has a floor, the polar regions have land. Deserts still contain air, heat, texture, and the presence of life. The void is like a desert stripped of context. It removes every point of reference, and that makes it difficult for the human mind to stay grounded when imagining it. People sometimes describe their reaction to cosmic emptiness using terms like too big, too quiet, or too empty, even though these descriptions are imprecise. What they truly mean is beyond what the brain can comfortably model. The brain evolved for movement across landscapes measured in steps, not in millions of light years. When confronted with a structure like the Boots void, the brain tries to scale it down, to translate it into something familiar. But the numbers resist scaling. The distance between two galaxies inside the void cannot be related to anything in daily life. The brain tries anyway, fails, and produces a sensation that resembles fear, but not quite. More like cognitive disorientation. This disorientation becomes even stronger when people imagine themselves as observers inside such a region. If you picture yourself living on a planet within a void galaxy, the night sky becomes a landscape of missing information. You would see your own stars. Perhaps you would see a handful of distant galaxies, but most of the sky would be empty. You would have no reason to assume the universe contains dense clusters. Your worldview would be shaped by silence rather than by structure. The idea of discovering the larger universe from such an isolated perspective highlights how deeply environment influences understanding. Thinking through this scenario makes people appreciate how much their own sense of cosmic scale depends on living in a moderately dense region, rather than in one of the universe's deepest hollows. People also experience a more philosophical reaction when contemplating the void. It raises questions about significance, scale, and the nature of existence. Some people interpret the void as evidence of the universe's indifference. Others see it as a reminder of how small the human realm is compared to the cosmic one. These reactions are not irrational. They stem from the mismatch between human timescales and cosmic timescales, human spaces and cosmic spaces, human quiet and cosmic quiet. The Buddha's void forces a confrontation with perspective. At the same time, the void also reveals something reassuring once the initial unease settles. It shows that emptiness is a natural part of the universe's structure. It is not hostile. It is not dangerous. It is simply a region where matter did not accumulate. Its presence helps shape the cosmic web. Its emptiness is not a flaw in the universe. It is part of what makes structure possible. Without voids, clusters would not stand out. Without emptiness, gravity would not gather matter into galaxies as efficiently. The void becomes, in its own way, a reminder that absence and presence both have roles in shaping the universe. Thinking about this balance can help ease the instinctive discomfort. When people imagine the void not as a threatening emptiness but as part of a larger pattern, the emotional reaction changes. The void becomes a feature, not a flaw. It becomes something that helps explain why galaxies form the way they do. It becomes a piece of architecture rather than a blank space. This shift in perspective mirrors what astronomers experience when they move from their initial awe to a more grounded understanding. The void becomes manageable once it is integrated into the larger picture. Another aspect of the fear of cosmic silence comes from imagining time rather than space. The void is not only vast in distance, it is vast in duration. A galaxy inside the Booty's void could go billions of years without encountering strong external forces. Its evolution could remain quiet for periods far longer than anything humans can conceive. Even thinking about such timescales produces a kind of temporal vertigo. The human mind is built for understanding years and lifetimes, not billions of years. The void stretches that concept of time and forces the mind to try to expand its understanding. Yet, even this challenge carries meaning. It pushes people to realize that the universe operates on scales that do not fit into everyday experience, and that this mismatch does not make the universe frightening. It simply makes it large. Much larger than human intuition can easily grasp. That realization often brings with it a kind of calm. The void becomes not something to fear, but something that represents the true size of the universe. There is also a psychological effect that comes from comparing the void to the human search for company and connection. Human societies thrive on proximity. People live in villages, towns, and cities. They form groups and networks. They rely on others for survival. Imagining a galaxy alone in a void resonates with that instinct. The solitude feels unsettling because it contradicts the instinct to seek community. But the galaxy is not a living being. It does not feel isolation. The projection comes from human tendencies, not from the galaxy itself. Recognizing this distinction helps ease the emotional reaction. Some people find the void calming rather than frightening. They see it as a place of stillness rather than emptiness. They interpret the absence of galaxies as a form of space where nothing is rushing, colliding, or burning intensely. They picture it as a quiet background to the drama of cosmic evolution. For these people, the void becomes a symbol of serenity, a place where the forces of the universe take a gentle form. This demonstrates how diverse human reactions can be. What unnerves one person comforts another. Regardless of the emotional reaction, the Buddhist void sparks introspection in almost everyone who learns about it. It encourages people to reflect on their place in the universe. It brings out questions about existence, scale, and meaning. It pushes the mind to expand beyond daily experience. It shows that understanding the universe is not only a scientific journey, but also a psychological one. The vastness that seems intimidating at first can become a source of grounding once the mind adapts to the scale. When people first hear about the Buddhist void, they often react with surprise, then with curiosity, and eventually with a question that sounds simple, but sits at the centre of why astronomers study this vast hollow so carefully. Why does something so empty matter at all? If the universe contains regions filled with galaxies, clusters, and dazzling structures, why spend so much time examining a place with almost nothing inside it? The answer turns out to be larger and more important than it seems. The Buddhist void matters not because of what it contains, but because of what it reveals. Emptiness is a part of the universe's architecture. More than that, it is one of the clearest windows into the processes that shaped the universe from the beginning. The void's silence holds information that dense regions often hide. Its stillness exposes patterns that can be hard to see elsewhere. Its scale makes it a powerful test of theories that describe how matter, energy, and space interact. To understand why this is true, it helps to begin with a simple observation. The universe we see today is not random. It has structure. Galaxies form patterns. Clusters connect into filaments. Filaments trace the shape of a cosmic web that spans unimaginable distances. This web is not chaotic. It is the result of laws that took effect seconds after the Big Bang. Those laws created tiny variations in density. Those variations grew under gravity. And from that growth emerged all the structure we see today. Every dense region, every filament, every cluster, and every void tells a part of that story. But voids tell the story in a way that is simpler and more transparent. Dense regions are complicated. They contain dynamic forces, interactions, collisions, and extreme environments. Voids are quiet. Their evolution is cleaner. When astronomers want to understand how initial density fluctuations grew into cosmic structure, voids become ideal places to study the process. The Buddhist void, being one of the largest known, becomes a kind of magnifying lens for this purpose. Its size exaggerates features that are subtle in smaller voids. Its boundaries show sharp contrast that reveal how matter flows in the cosmos. The few galaxies inside it show how systems evolve when external forces are almost absent. The void acts as a natural laboratory where the most basic cosmic processes can be observed without interference from complex environments. One of the first reasons this matters is that voids help test cosmological models. Modern cosmology relies heavily on simulations. These simulations begin with early density fluctuations derived from observations of the cosmic microwave background radiation. Then they apply the laws of physics to show how the universe evolved over billions of years. When astronomers compare these simulations to the real universe, they look for how well the large-scale structures match. Do the filaments appear in the right places? Do the clusters have the right mass? Do voids have the right sizes? This last question is particularly important. The distribution of void sizes is sensitive to the underlying physics. If voids in simulations do not match voids in the observable universe, then the models need adjustment. The Buddhist void plays a crucial role in this comparison because of its extreme size. Its existence tests the upper limits of what simulations can produce. If simulations consistently fail to produce voids as large as Buddhist, then cosmologists must reconsider assumptions about dark matter, dark energy, or the initial conditions of the universe. But if simulations can reproduce it, then the void becomes a confirmation that our understanding of cosmic evolution is on the right path. The Boots void sits right at that boundary between rare but possible and uncomfortably unusual. Studying it helps define where that boundary lies. Another reason the void matters is because it highlights how matter flows through the universe. In dense regions, matter follows complicated paths due to gravitational turbulence. In voids, matter flows more smoothly. Tracking galaxies near the void's edges helps astronomers measure these flows. These measurements reveal how quickly the void expands, how the surrounding filaments grow, and how gravity and expansion interact. This information helps refine estimates of the universe's overall expansion rate. It helps test the behavior of dark energy. It even helps evaluate alternative theories of gravity. The void becomes more than a region of emptiness. It becomes a tool, one that pushes theories toward greater accuracy. The Bootis void also helps astronomers understand how galaxies evolve in different environments. Galaxies inside dense clusters evolve through frequent interactions. They merge, they collide, they lose gas, they undergo gravitational distortions, their shapes become complex. In contrast, void galaxies evolve slowly. Their behavior reflects internal processes rather than external influences. By studying these galaxies, astronomers create a clearer picture of how much a galaxy's development depends on its environment. This comparison helps answer questions about why some galaxies form spirals and others form ellipticals, why some remain blue and others turn red, why some continue forming stars while others stop early. The void provides a clean environment for studying these differences. Without its isolation, the influence of external factors would complicate the picture. The Bootis void gives researchers an environment where internal physics shine through more clearly. Another reason the void matters is because it provides clues about dark matter. Dark matter is invisible and cannot be measured directly. Instead, astronomers study how it affects the motion of galaxies and the distribution of matter. In dense environments, these effects are complex, but in voids, dark matter behaves more simply. Its low density makes patterns easier to interpret. The distribution of dark matter around the Boots void reveals how dark matter flows relative to ordinary matter. It shows how gravitational forces act in low-density environments. These observations help refine models of dark matter behavior, which in turn helps refine models of galaxy formation. The Bootis void also matters because it helps test the behavior of dark energy. Dark energy drives the accelerated expansion of the universe. Its effects become more noticeable in empty regions than in dense ones. Voids expand faster than other regions because gravity has less material to counteract the expansion. By measuring how quickly the Bootis void expands, astronomers gain insight into how dark energy behaves across space. If voids expand at rates inconsistent with predictions, it could reveal something new about dark energy. This is one of the most important areas of modern cosmology. The Boots void provides a powerful observational case for these tests. Another important contribution of the void concerns the large-scale distribution of galaxies. The cosmic web is not uniform. Some regions are dense, others are sparse. The Bootis void sits at the extreme end of that spectrum. Understanding why it formed, how it grew, and how it interacts with surrounding structures helps researchers understand the distribution of galaxies throughout the universe. It clarifies why some regions contain clusters while others remain empty. It shows how initial conditions lead to long-term patterns. These insights help solve larger questions about how galaxies came to be where they are today. The void also highlights the importance of randomness in cosmic evolution. The early universe contained tiny variations in density. Some of these became the seeds of galaxies, others became the seeds of voids. The Bootis void represents one of the lowest density initial fluctuations. By studying its history, astronomers better understand how rare events in the early universe shaped the large-scale structure we see now. This helps explain why some areas became rich with galaxies, while others became almost empty. The void becomes a fingerprint of the early universe, preserving information about conditions billions of years ago. From another angle, The void matters because it helps show that cosmic structure is not uniform. This may seem obvious, but it has far-reaching implications. If the universe were uniform, galaxy formation would follow simple patterns. Instead, the universe is full of complexity. Some regions are dense, others are sparse. This variation affects everything from the timing of star formation to the growth of black holes. The Bootes void exemplifies this complexity. Its extreme emptiness makes it a useful case study for understanding how that variation shapes the universe. Another reason the void matters is because it helps rule out speculative explanations about the universe's structure. For example, some theories propose that the universe might have large-scale directional biases or unusual symmetries. If that were true, voids would form differently. Their shapes, sizes, and distributions would not match what we observe. Studying the Bootes void helps confirm that the universe is statistically uniform on large scales. The void fits within expected patterns. It does not indicate any exotic symmetry or strange large-scale effect. This reinforces the standard model of cosmology. The void becomes a piece of evidence supporting a broader understanding of the universe. The Bootes void also matters because of how it challenges perception. Its size forces astronomers to check their assumptions. It encourages careful measurement. It reminds researchers that improbable structures can exist even in a universe governed by simple laws. These reminders prevent complacency in scientific thinking. They push researchers to refine methods and tools. They encourage deeper analysis. Without extreme structures like the Bootes void, the range of cosmic possibilities might be underestimated. Something else that makes the void important is the way it affects its surroundings. The Bootes void shapes the dynamics of its region. It influences how nearby filaments stretch. It affects how clusters grow. It contributes to the motion of galaxies at its boundaries. All these effects matter for understanding how the cosmic web evolves. The void's presence influences a region hundreds of millions of light-years wide. Understanding this influence helps piece together the complex interplay between emptiness and structure. The void also helps clarify the role of environment in cosmic evolution. It demonstrates that environment matters just as much as internal properties. A galaxy's fate is determined not only by its mass, composition, or rotation, but also by where it lives. The Bootes void shows what happens when a galaxy evolves in a quiet place. Cluster regions show what happens when a galaxy evolves in a busy place. Together, these environments help build a complete picture of galactic evolution. Another reason the void matters is because it provides a contrast that makes dense regions easier to understand. Without voids, the differences between structures would be harder to detect. The boundaries between empty and dense regions highlight the shape of the cosmic web. They reveal how matter accumulates. They show how gravity dominates in some areas and expansion dominates in others. The void enhances these contrasts, making the patterns more visible. The Bootes void matters for one further reason that is less technical but deeply meaningful. It helps remind people that the universe is not built to match human intuition. It is larger, more complex, and more varied than instinct suggests. This realization expands perspective. It encourages curiosity. It reveals that emptiness itself has purpose. In this way, the void becomes not just a scientific structure but an educational one. It teaches that silence has shape, that nothing can hold meaning, that absence can reveal patterns hidden behind presence. After travelling through the Bootes void in thought and following its strange shape through space and time, the mind eventually begins to drift back towards something familiar. Not because the void loses its hold on curiosity, and not because the ideas around it fade, but because reflection naturally pulls a person back toward their own world. Even when exploring something unimaginably large and remote, there comes a moment when the imagination returns to the human scale. And that return, when done gently, becomes a kind of soft landing. It is the point where everything learned about emptiness settles into place, not as something distant, but as something that contributes quietly to understanding the universe as a whole. Coming back from the edge of the void does not erase its strangeness. It simply places that strangeness in context, where it becomes easier to hold. The Buddhist void is so large that a person can spend hours picturing its shape and still not fully grasp it. It stretches across hundreds of millions of light years. It contains nearly nothing by cosmic standards. It sits within a structure that looks almost like a bubble carved out of the universe. Thinking about such a place brings out a complicated mix of emotions and ideas. There is surprise that such an empty region can exist at all. There is curiosity about how something so vast forms. There is a kind of quiet astonishment that humans, living on a small planet circling a modest star, can detect, measure and map such an expanse. And somewhere inside all that, there is something softer, a sense that emptiness, rather than being frightening, can be a kind of anchor for reflection. Returning from the void means taking these feelings and bringing them back toward the scale of everyday experience. It means recognizing that the universe is full of extremes, and that one of the reasons to study a place like the Buddhist void is to understand how those extremes fit together. Dense regions show one side of the universe, empty regions show the other. Together they make a pattern that is more complete than either would be alone. This realization makes the return feel less like leaving something behind and more like integrating it into a broader picture. As the mind moves back toward familiar reality, one of the first things it notices is the contrast. Life on Earth is shaped by presence. There are sounds, landscapes, temperatures, people, and constant motion. Even moments that feel quiet carry layers of activity. Leaves shift in the wind, water flows, machines hum in the distance. Human life is surrounded by signals and cues that remind the mind of the world's familiarity. Coming back from the idea of a region where almost none of those cues exist makes the familiar feel richer. It sharpens awareness of how much detail fills every corner of daily existence. At the same time, it also changes how the universe is perceived. Before learning about the Buddhist void, many people imagine space as mostly empty. After learning about the Buddhist void, they realize that most of space is only relatively empty. The void elevates the concept of emptiness to a scale that redefines what empty means. It shows that even the dark spaces between galaxies are not as empty as this vast region where almost nothing interrupts the silence. Returning from that understanding leaves a person with a renewed sense of nuance. Emptiness becomes something with degrees rather than something absolute. Another part of this soft landing involves remembering that even the most extreme cosmic structures are part of a coherent universe. The Buddhist void is not an anomaly in the sense of being out of place. It is rare, but it is not disorderly. It formed through the same processes that formed everything else. It evolved under the same laws. Coming back toward everyday thinking with this in mind produces an unexpected calm. The more one understands about the universe, the more the extremes seem connected, and the less disorienting they become. What first looked like an inexplicable whole becomes a predictable part of a grand pattern. Understanding replaces the instinctive discomfort with a grounded sense of how things fit together. It also becomes easier to appreciate that the universe is not a place where everything must be filled. Emptiness is not an error. It is a necessity. Without empty regions, dense regions would not grow. Without voids, clusters would not form as they do. Without space to expand into, the cosmic web would collapse into a uniform haze. Reflecting on this helps create a sense of balance. It allows emptiness to be seen not as an absence, but as part of a larger structure that supports the universe's development. This shift in perspective is part of what makes the return from the void gentle. The mind no longer treats the void as something alien. It becomes part of the foundation for understanding how the cosmos works. There is another aspect to this return that has more to do with human psychology. When people confront something overwhelmingly large or unfamiliar, they often pause afterward to reassess how they feel about their own scale. Learning about the Buddhist void can create that pause. It invites comparison between the cosmic scale and the human scale, but this comparison doesn't always create insignificance. It can instead create clarity. Understanding that humans live within a universe containing structures far larger than imagination can easily hold reminds them that perspective changes meaning. Smallness can feel limiting when viewed one way, but it can also feel grounding when seen through the lens of understanding. Being small in a vast universe can foster humility without diminishing value. As the mind continues drifting back from the void, it becomes easier to reflect on how such knowledge enhances curiosity. Learning about the Booty's void opens up questions rather than closing them. It encourages people to ask how many other extreme structures exist. It brings up thoughts about how the universe organizes itself. It sparks interest in how galaxies live in different environments. This curiosity does not stay out in the void. It comes home with the person thinking about it. It becomes part of how they look at the sky, how they think about distance, how they understand the place Earth occupies in a vast cosmos. Part of returning smoothly involves acknowledging that the void's emptiness is not a place to escape from, but a region to observe with the same calm attention given to any other natural phenomenon. The edge of the void becomes something like a boundary between two modes of thinking. On one side is the boundless scale that challenges the mind. On the other side is the familiar world where concepts can be held more comfortably. Moving between these sides expands understanding rather than straining it. It allows the mind to move fluidly from the vast to the personal. Another part of this gentle return comes from remembering that even though the Boot's void is extreme, it is not unique in kind. Many voids fill the universe. Some are smaller, some are larger, some are more elongated, some are almost round. They form part of the architecture that supports the cosmic web. Thinking about them all together makes the Booty's void feel less like an isolated feature and more like a member of a larger family. The extreme examples help illuminate the rest, just as the rest help contextualize the extremes. This realization reduces the sense of isolation that initially accompanies thinking about such an empty place. There is also a reassuring quality to knowing that human technology allows the study of such distant regions. The mere fact that people can map a void hundreds of millions of light-years wide shows that curiosity and exploration have reached extraordinary levels. Coming back from the void with this awareness gives a renewed appreciation for science itself. It reminds people that their tools and methods allow them to extend their understanding far beyond their immediate environment. This sense of connection to the greater universe becomes part of the soft landing. As thoughts return more fully to the familiar, another change takes place. The night sky begins to look different. Before learning about the Boot's void, a person might look up and see stars scattered randomly. After learning about the void, the stars become tiny markers of a structure that stretches across unimaginable distances. Each point of light becomes part of a larger pattern that extends into filaments, clusters, and hollows. The sky becomes a map rather than just a backdrop. This new perception does not overwhelm. It enhances. It provides a sense of belonging to a universe that has shape, history, and depth. Returning from the void also highlights a simple truth. Even though the void is enormous, Earth is not anywhere near it. The solar system sits in a comparatively normal patch of the cosmic web. Galaxies are present in every direction. Local star groups interact. The Milky Way belongs to a small cluster, which sits along a filament, which connects to larger structures. This awareness brings out a sense of home, not in the sentimental sense, but in the grounded sense of knowing where one stands. Earth is part of a region shaped by balance rather than extremes. This recognition makes the return feel stable. Yet the mind rarely leaves such a journey without carrying something forward. Knowledge of a place like the Boot's void lingers. It becomes a reference point for understanding other cosmic features. It adds depth to conversations about space. It influences how people think about scale, emptiness, and structure. Even though the void remains far away, It becomes part of the mental landscape, and each time a person imagines it again, the return feels smoother. Coming back from such ideas also invites reflection on how humans interact with silence. Silence in daily life is often welcomed. It provides rest, focus, and calm. The silence of the void, though unimaginably deeper, shares a similar quality once the initial unease fades. It becomes something that represents steadiness rather than threat. The more a person thinks about it, the more that silence becomes a reminder of the universe's balance. It shows that not every region must be filled with activity or noise for it to hold meaning. As thoughts settle further, the return from the void feels less like stepping back and more like integrating a new perspective. The idea of emptiness becomes a way to understand fullness. The idea of silence becomes a way to understand structure. The void becomes not a distant curiosity, but a piece of the universe that contributes to the entire pattern. And as all of this comes gently together, the mind finds itself ready to move forward again into whatever comes next, carrying with it a quiet understanding of how even the deepest emptiness can deepen the sense of connection to the universe as a whole.